Progress.
Okay, good morning, everybody, and welcome to this 16th edition of BICA conference. It's a pleasure to see so many people, so many brilliant minds together here today, united by our shared fascination on BICA, and also with BICA potential in our lives. Over the next few days, we will explore forefront of BICA research. We will learn about theoretical foundation and technical advances that influence our relationship and society. We will hear from leading experts from around the world about their thoughts, their ideas on aging. Their insights will surely spark discussions, proposals, and cooperative work and during and after this conference. For those unfamiliar with BICA term, BICA stands for Biological Inspired Cognitive Architecture. In other words, is a way to build agile systems. Well, this is important not just because it's a way to implement this kind of system, but rather because the way in which those systems influence our life. This conference will explore diverse facets of BICA for implementing agile system, as I said, to including its potential in foundings in cognitive science, and this for solve complex human problems. We will hear some of I want to say more more practically, but
you're doing it for
from
Mexicans?
different expert people that is expert in this field from around the world. Surely, they thought and ideas will make start different proposals, and I hope cooperative work between all those brilliant minds that we are together here in this conference. Well, those experts will help us to understand current challenge in implementing agile systems with BICA, obviously, as well as the benefits of those systems for the humanity. I am very enthusiastic to be part of this gathering, and I am confident that this BICA 2025 will provide an opportunity to learn, share, and start significant collaborations in this fascinating field of BICA. I have no more words that say that let's start at this moment, 9:10, the conference. And we will start this conference with a talk from one of our keynote speakers, Dr. Kugel, who has worked over a decade as software engineer. But what for me is quite interesting is that his background, he has a very solid basis on mathematics and how can say that neuromorphic? No, anthropology. Anthropology. And if you remember, anthropology is one of the 6 main areas of cognitive science. So this talk obviously will introduce us in this fascinating world of BICA systems. But before he starts his talk, we need 5 minutes to prepare the stage. Okay? So please, 5 minutes.
Okay, great. Well, hello everybody. This is so exciting to be here and to help to kick off BICA with this first keynote talk. So I'm going to go a little more into my background, but I think Felix did a pretty good job of covering all the important details. Maybe I'll add a couple more things. So this keynote, I'm going to be focusing on BICAs for science. There's science and engineering pursuits with BICAs. I'm going to be focusing on scientific pursuits. There's a lot of this. I'm going to say that I haven't figured it all out. I haven't figured out AGI minds yet and built these, but so there's a little bit of speculation involved in this, some discussion of preliminary work that I'm doing, and maybe a little bit of philosophy of science that goes on in here as well. But hopefully this will be an interesting case study for everybody to hear about. And if all else fails, I've got palm trees inspired by this beautiful locale, both of the natural and artificial variety. And I try to put at least one palm tree on each slide. So if nothing else, you've got that to look forward to. Okay, so a little bit about myself and some cute little pictures here. So as Felix mentioned, I spent some time as a software engineer. I was working for Northrop Grumman, and then later on I worked for FedEx in various capacities, engineer, architect, things like that. But fortunately, I found my passion later on in my career, and I became a cognitive scientist, decided to go back, and I worked with Stan Franklin for quite a while. Currently, right now, I'm actually at a small liberal arts college, actually, in Memphis, Tennessee, called Rhodes College. and I'm an assistant professor in the computer science department there at Rhodes College. But for the last 13 years, this is the most important part, is that I've been focusing on the LIDA cognitive architecture. Starting back in 2012, Stan Franklin really got me passionate about cognitive science and cognitive architectures. I took a class from him called Control Structures for Autonomous Agents, which is a definition of mind according to Stan Franklin. That's what he would define minds as, is control structures for autonomous agents. So I worked with him for 13 years. Unfortunately, he did pass away back in 2023. And here's some pictures of the group over here. So this goofy little guy here, that's me. And then Stan Franklin's in the bottom right of that picture. And then in the left one, this is me with my wife over at the coast of Oregon. So I included my dissertation title here because it's really relevant for this talk. So this talk is about mental imagery and consciousness and also this condition called aphantasia. And my dissertation was really focused on these kinds of things. So embodied simulation-based cognition, a hybrid approach. So the mental imagery part is simulation-based, kind of emerges from that. And then the hybrid approach, I think a lot of cognitive architectures are kind of going towards a hybrid approach where you combine connectionist and symbolic techniques. And so that's what my dissertation was on, and so has bearing on what we're going to go over. Oh, and by the way, today's my birthday. Okay, so the first thing I want to do is clarify, so cognitive architecture, the term can be used in different ways. And so I want to really kind of say that I'm a true believer in this original vision that Alan Newell had, this idea of unified theories of cognition. A little part of me says maybe we won't get there in my lifetime, but that doesn't mean I'm not going to strive for it. So I believe that cognitive architectures should strive to be comprehensive, try to do every single functionality, find that single set of mechanisms that can explain all kinds of behaviors, every behavior, and to really do the entire system, build complete systems, and try to solve problems like that. So that's my dream, that's what I'm striving for. This is partly given to me by Stan Franklin, the passion that he kind of inspired me at this. But I have a little snippet here. This is a figure that appeared in Alan Newell's 1994 book, Unified Theories of Cognition. Areas to be covered by Unified Theory of Cognition: problem solving, decision making, routine action, memory, learning, skill, perception, motor behavior, language, motivation, emotion, imagining, so forth and so on. So it's all there. It's all there. And there's the ... at the end. So if you can think of other stuff, you slap that in there. And that's my dream too, is to go over all of these things. Okay, so one of the things we want to do with cognitive architecture is why they sort of transcend just cognitive models, is that we can build systems and we can learn from building systems, the synthetic approach. So we build autonomous agents. So Stan Franklin and Art Gracer came up with this very, very well-known definition now of autonomous agent. It's a system situated within and part of an environment that senses the environment, acts on it over time in pursuit of its own agenda so as to affect what it senses in the future. That's a really good definition. That's something that I think captures the sort of the most important aspects of the systems that we're trying to build. And the thing that's kind of nice is that if you look at something like a large language model-based chatbot, it's not an autonomous agent according to this definition. So in Stan Franklin and in my mind is that these aren't minds, large language models. Okay, so cognitive architectures, there's two different paths that you can take with these. There's an engineering path of building useful systems, and then there's the scientific path, and that's the path that I'm most interested in talking about. So I think the most opportunities are here in this science path. I think that combining the interpretability of these systems that we build, we can see and understand what's going on. They're not necessarily black boxes like these other systems. And just the biological inspiration, pulling things from psychology, neuroscience, all these different areas. I think this is an extremely fruitful area for BICAs, and this is what the talk is going to be focused on, is this aspect. And so going to that, so now I'm going to sort of transition over to opportunities, challenges, and some methodologies for BICAs in science. So this diagram here appeared in Stan Franklin's book, Artificial Minds, and it tries to characterize these different ways of converging on an understanding of mind. So mind is here in the middle, and you have these different sort of axes, top down, bottom up, analytical, synthetic approaches. So I think we actually kind of combine all of these things in the stuff that we do with cognitive architectures, right? So with the analytical approaches, so typified by something like psychology or neuroscience, we look at existing natural systems. We try to distill these systems into some understanding of them, models, rules, concepts. We take all of that stuff in this analytical approach, and we build a theory from it, a theory of mind. We can do this in a top-down way where we're looking at, say, behaviors and trying to distill these things into models, or we can do it in a bottom-up approach, and we can look at the mechanisms that underpin the systems, the neural substrates of the systems, try to get understanding of that. All of this sort of fuels, again, our understanding of mind from an analytical perspective. And then there's this interesting thing that's, I think, a little bit unique to our work, is that we can take these theories then and we can build systems. We can see what they do. You know, what is our theory? You know, what are the behaviors that manifest from the system if we were to build those things? And then we can experiment on this stuff. So I think we combine all of these different things when we do BICAs right, when we use them right. So in my mind, the dream that I would like to get to is something like this sort of virtuous cycle where we have a target species, and most of us may be interested in humans, but any target species, there's no reason why we couldn't do non-human animals and think about those as well. So we study the species. We build our theory from that species. From the theory, we create some kind of an artificial version that sort of exemplifies what that theory means. And then we observe it and we generate novel hypotheses from this model species. And from there, we validate that back on the target species, and the cycle continues. We refine our theory. This is the way I see that BICAs should be used. This is sort of my dream of where I want to go. And I'm sure that maybe I'm saying things that other folks maybe have already thought about and agreed with. But trying to get there is kind of what I'm trying to understand. And so by theory, of course, what I'm talking about is our cognitive architectures. That's the theory that sort of distills the stuff. Okay, so again, there are analogs to this in biological research, right? We have all of these different model species that we use to try to understand humans better. Are they exactly humans? No, but they have properties that we're interested in studying because we believe those things will generalize to humans. If we're doing some kind of pharmacological research, whatever it might be, maybe even behavioral studies, we can use these model species and then we can learn from them and hopefully generalize to humans. And then so you've got C. elegans, kind of a roundworm, type of nematode, Drosophila. We've got basically our common house mouse, and then we have this machina cogitans, or thinking machine. That this is, I think, what we're all trying to get to, build and try to sort of converge this to something that is as human-like or animal-like as possible, naturalistic as possible. So the challenge is that, so in biological research, and I pulled this from a biological research paper, we have this idea of external validity, right? So the idea is this, so I'll just read this. External validity is the extent to which research findings derived in one setting, population, or species can be reliably applied to other settings, populations, or species. So what we want to be able to do is we want to be able to look at our artificial minds and have confidence that when we do experiment on these minds, when we learn something from observing their behavior, that we can learn something that will actually apply towards humans. And so trying to maximize this external validity, I think it's something that we should all think about when we're designing our experiments and trying to, again, maximize the chances of generalization. So actually, I'll go back for a second. I'm not sure if I can ask the audience questions here or not, but so all these other species that we're talking about here, they appear very different to humans, right? So why is it that we believe these have some external validity? Why do we believe we're going to be able to generalize from these species to humans? Well, evolution, right? We share more than 3 billion years of evolution with these species. And so that's kind of where we get this, this belief that things are going to generalize from these species, but it doesn't always work, and a lot of times it fails. So we need some kind of a grounding for our thinking machines as well to get that external validity. So this is kind of what I've been thinking about, is how to maximize external validity in the experiments that I do, and that way I have some confidence, hopefully, that my results will generalize. This is sort of the philosophy of science, part of all of this stuff. So there are 4 different aspects that we kind of need to consider, and there's probably more, but this is something that I'm sort of thinking through. So control structures, and this is something I talked about before. People that are familiar with Alan Newell's work, like Can't Play 20 Questions with Nature and Win, and this is also in Unified Theories of Cognition. He defines that. I'm going to go into that in a second. Environments. Environments are an important part of determining behavior. So controlling for the environment and differences, that's important. And there's also, our natural species, the things that humans, we are not blank slates. We have evolutionary heritage. We've got things that we come with. And so understanding what that stuff is and how it might change the behavior of the system, that's important. And then also, humans in particular, we're social creatures. So we've got this cultural aspect that will dictate our behavior as well. So we'd like to try to say, at least substantiate when we're trying to defend our models, to say, when I'm doing an experiment with this thing, these things either are unnecessary, that we're controlling for those, the environment is similar enough, evolution, developmental, experiential histories, this is something that's not critical for this particular, where we feel like we've replicated some part of that. And then the social and cultural context. So we're trying to control for these, and then we're playing with our control structures. So this is our degree of freedom, and this is really kind of where we're trying to figure out our minds. So again, going back to Alan Newell, there's this quote from Can't Play 20 Questions with Nature and Win. As long as the control structure, the glue is missing, so long will it be possible to suggest an indefinite sequence of alternative possibilities for how a given task was performed, hence to keep theoretical issues from becoming settled. So this whole paper, one of the things he was meditating on was, how do we advance science of the mind? What do we need to do in order to do that? And he was saying that control structures, that's the thing that needs to be specified. So he gave it as a programming analogy. So he said control structures are the sequences of executable statements and conditional operations that determine the system's behavior. Basically, it's a behavior-producing program. And by specifying all those different executable statements and conditional operations, we constrain the design of the system. We're making an assertion. This is the theory. We're saying this is something that is invariant in the system. This is something that I'm sort of defining my theory of mind around. This is something that will constrain how all the different components of the system work together. So control structures, this is, again, what Stan Franklin said, minds are control structures for autonomous agents. That was one of the definitions that he threw out, and it gives a nice intuition for it. These control structures, this is sort of where we define how things fit together, and it's an assertion that we make that needs to be defended. And Stan would also say that control structures, or minds in general, their main purpose was to answer this question of what do I do next? So again, sort of gives the intuition for what control structures do. Okay, so in establishing whether one system that is meant to replicate human cognition or model salient aspects of human cognition, to say whether it does it well in a way that's sort of faithful to the whatever system you're studying, the natural system, Turing test is not enough. That's become very, very clear. And in some respects, I think that Turing was not even making the statement that it was enough. If you read the paper that the imitation game was proposed in, there's a section where he says, is it not possible that a machine may basically think in a very different way than man does, but still be a thinking machine? It's like, well, that's a relevant point. Yeah, it could think very differently, but he wasn't concerned with that. He just wanted to be able to do thinking machines, not to say it should be like humans think, just that to prove that, yes, machines can think. And so it was a different objective, but when you're trying to figure out whether the control structures of the system are similar enough to humans or whatever system you're studying, Turing test is not enough. And these data-driven approaches that are currently out there, throwing terabytes of data in order to kind of figure out this function approximation for the mapping of behavior. From a scientific perspective, this is not enough. This is not a good way to go. You have to have some kind of a theory that, like Alan Newell says, constrains the operation of the system. Your control structures constrain the operation of the system. So there may be many, many system designs that will work to solve some problem, but there's only a small number of them that are going to be sufficient for scientific pursuits. So long story short, we need a theory. We need cognitive architectures. Environments. So again, this is from Herbert Simons. I think this is the third edition of The Sciences of the Artificial. An ant, when viewed as a behavior system, is quite simple. The apparent complexity of its behavior is largely a reflection of the complexity of its environment. And so there's this example that he gives in The Sciences of the Artificial, where he talks about tracing the path of the ant. And it's very meandering. You couldn't tell whether it was an ant or whether it was a downhill skier. You have no clue, but really this is a reflection of the environment. So there's this deep reflection of between the environment and the organism. The two are coupled. And so this is something we have to be careful of in our experiments, because if everything else is equal, you had exactly the same minds, you had exactly the same social and cultural aspects, all those different things, you controlled everything perfectly except for the environment, how much of a difference in the environment would be enough to induce a difference in behavior? So that's a question of, well, okay, so if you get different behavior in your system, does that necessarily mean that your control structures are different? Not if the environment can change. And so you see all these different attempts these days. So sim to real, this is something that there's a lot of interest in the broader machine learning, reinforcement learning. You train in your virtual space and you try to transfer this over into your real space. But the problem is, if there's too much of a discrepancy between the two, you go over from the virtual space to the physical space, and then you end up running over this person in the sidewalk because something was just not quite the same, right? So this is a real problem, but the point of it all is that environments matter. Differences, even if it seems like it's a subtle difference, matter. And these differences could happen for a lot of different reasons, right? So the physics could be different, materials that you're dealing with different, lighting, stuff like that. I mean, you can see differences just in these two over here. But the more subtle thing is sensory modalities. If you look at something like humans, how many different senses do you have that aren't modeled in these environments? And so if you're trying to get a holistic picture of humans, most of our virtual environments these days just don't cover everything that needs, in a lot of cases, vision is not enough. For example, walking. If you wanted to program a robot to walk, if you don't have something like proprioception, it's a lot harder. If you wanted to walk across the room and you lost your signal from your body, it would be extremely difficult. So that's another one of the divergences that could happen. And also action affordances too, things you could do in the environment. So I just did a search, so since 2024, on sim to real gap, there was 4,800 hits. This is, again, really a big area of interest right now, because people would like to be able to just use simulation completely and then just transfer to the real world, but we're not quite there yet for a lot of tasks. Okay, so next thing up is force correspondence. We aren't blank slates. We have some behaviors that come to us, maybe in the form of these different reflexes that were given by evolution. So we've got this rooting reflex. I think this one is called a Murrow reflex. The baby thinks it's falling, and so it reaches out. But we come with this stuff. And the question is, how deep does this go? How many of our cognitive biases come from evolution? So trying to figure out what those things are, that's something you either need to kind of figure out it's not relevant for the kind of experiment that I'm doing, or somehow figure out a way to replicate that kind of stuff. Humans, we think of it as like, oh, we have this one snapshot of a human, or this sort of prototypical human, but we all change over time. We all age, we are different over time, and trying to figure out what matters and what doesn't matter for our experiments. And then finally, we learn stuff, right? We learn stuff. And so all of our life experiences, those sort of coming in. So humans are very, very complicated, and trying to control for all these things can be quite challenging. And finally, social and cultural contexts. going to go too far into this, but obviously we have interactions with other people, right? And the societies that we're in, they give us values and beliefs and norms. All these different things influence our behaviors. So we have some for social context. There's some very interesting research that's been done about, for example, diffusion of responsibility. When you're in a group, if you have somebody that's screaming for help, it's a large group, you might say, well, somebody else has got this, not even gonna bother. Same thing with this risky shift here. When you have a group of people, you especially see this with some younger people, you get into a group, they might do some really crazy things that they would never have done without that group dynamic. So there's a lot of different influences to behavior, and then trying to sort of control for these things. It's something to at least be aware of anyway. Okay, so in summary, it's all of that stuff. This will be the end of the philosophy of science musings. So autonomous agents, we want to create these things, right? We want to create these things, and you can view these things as species of mind. The question is, how close is this species to your target species, humans, for example? It's best just to think of them, they are some species, and hopefully you think they're close enough. We want to experiment on these things because we want to learn something about humans. We want to do things to the model species and then find something new that we can verify against the target species. And by this virtuous cycle, hopefully we can converge to get our BICA agents to get ever and ever closer to our target species. So I've been talking about this idea of external validity, and this is really related to, can we generalize? Can the findings we have in experimenting on this thing and the environment that it's in with all the influences it has, can we say something about us, for example? And that's what we'd like to be able to do. And so controlling for environmental factors, experiential factors, and these different sociocultural differences, it's something to think about when you're trying to do science with a BICA. So now I'm going to talk about a case study that I've been working on for a while now with some of my students. So I'm going to go into mental imagery and this new thing that has sort of become a very hot topic, aphantasia. I say a new thing, it's sort of been rediscovered starting in 2015. It was sort of branded again, but the ideas or the phenomena was first understood or recognized back in the 19th century. Okay, so mental imagery, I don't know if everybody sort of already kind of knows what mental imagery is, probably would, but mental imagery is sensory-like experiences without a corresponding external stimuli. So you are able to have something going on in your mind that you're able to consciously experience, and it has some quality as if you were looking at or hearing or something else in the world, that thing, even though it's not there. So there's some different analogies, seeing with the mind's eye, hearing your inner voice, having a song stuck in your head, all these different things. I think some people may think these are metaphorical, but it's not just metaphorical. There really is an aspect of seeing internally or hearing internally. And the interesting is, and we'll go into aphantasia in a second, some people don't have the ability to do this, and it's actually maybe up to 3% of the population. So it's possible that somebody in here is an aphantasic. So the way I like to think about mental imagery, though, is predictions, the predictive aspect of it. So experience-based predictions. So here's a quote from Moulton and Coslin. Mental imagery allows us to simulate reality at will. Because of this, it allows us to predict what we would experience in a given situation or after performing a specific action, right? We learn how the environment works through our experience, and we can use that model of the environment to think about it, understand it. So this is the aspect of mental imagery that I'm really interested in because it leads to planning and all these important things that we do all the time. The nature of mental imagery, though, is still, I think, a little poorly understood. At least that's my sense of it right now, even though it's been studied for many decades. So this ability allows us to reconstruct the past, but also to anticipate what will occur in the near and distant future. So you hear some people use these terms, mental teleportation, which makes sense because if I wanted to imagine my home right now, it's not here, but I can imagine it. Mental time travel, what will I do tomorrow? I can imagine those things, but it requires some projection of myself in time. Mental images, consciously experienced, and this is one of the things that is exciting for me in my research with LIDA. So LIDA, one of the things that one of the theories it implements is the global workspace theory of consciousness. And so this gives me an opportunity to study conscious and unconscious counterparts, or conscious and preconscious counterparts. Mental images are analogous to the stimuli from corresponding sensory modalities. So what I mean is this. So if I were to ask all of you to imagine an apple, and you close your eyes and you're thinking about this apple, if I then said, zoom in on the apple so that it completely encompasses your total field of view, and all you can see is that. The way that we manipulate and transform these things mentally follows similar rules to when we're doing these things visually in the outside world, right? Same thing when we're trying to do things with songs. You have some temporal extent, and that's just going to exist in your songs. So there is some correspondence, whatever the nature of that representation is, there's some correspondence in how it's manipulated to our sensory modalities. And there is, when we look in psychological literature or neuropsychological literature, there is an interference that can be induced or will happen when sort of the same real estate is used in the brain. So if I am seeing something in the world and it is similar to the thing that I'm imagining, I might see priming effects. If there's differences, I might see interference. Another property is this rapid decay. So if I don't continue to maintain these images, they'll decay away. Stephen Coslin talked about 4 different fundamental operations of mental imagery. And he's a prolific writer on mental imagery. Talked about generation, so being able to either volitionally or just spontaneously from just a random thought, generate an image. So image generation is the formation process. Transformation is the process of manipulating that thing. So typical examples in the literature are things like mental rotations or translations, things like that, but it's anything that manipulates a already created image. Image inspection, this is where you're basically perceiving the thing and that you're basically looking at it or in some way, interrogating the image you've already got. So you're looking at the properties of the image or other things. And there actually seems to be a relationship between these two. And then maintenance, again, if you don't try to actively think about the same image again and again and maintaining and working memory, it will decay away and lose vividness and eventually go away. So these are, from an implementation standpoint, things that need to be implemented. Finally, more terminology. So object imagery and spatial imagery, this is important for aphantasia. So object imagery is related to form, size, shape, the properties, low-level details of an object. Spatial imagery is abstract, the location of the different parts of the object in space, so spatial extent in a gross way. And then there's a relationship between mental imagery and perception. This is controversial, but perception and imagery seem to use similar parts of the brain. This is a paper by Ganis, and Coslin is one of the co-authors of this one, where they looked at brain scans related to perception, brain scans related to imagery of the same things, subtracted off those neural patterns of activation, and they're trying to show that there's overlap. But again, this is controversial about total overlap. So one of the things that's really interesting about mental images is that it leans into this conversation about what representations do we have that we think with. So there are 2 big positions that have been batted around for decades, probably at least 40 years. And one of them is that we think exclusively with what's called descriptive. Also, this would be symbolic or propositional kinds of representations. So here we're saying we have a representation that's saying a ball is on the box. And so we have this kind of, again, it's sort of linguistic in this particular example, but the idea is that we have this sort of symbolic representation that we think with exclusively. But mental imagery brings in this idea that we actually have another kind of format that appears to be going on, which is depictive or imagistic. And so if you want to say the same thing as ball on the box, you can do the same thing with something that looks like an image and think with that kind of thing. So that's one of the interesting things about mental imagery is it fuels this debate. And here's another thing that Barceló is doing that's very similar, related to modal and amodal symbols. And it's very similar in concept. With modal symbols, you're extracting parts of a real experience that you have of the world. And then you're actually thinking with sort of this attenuated version of whatever that thing was that you experienced in the world. With amodal symbols, you are translating to an intermediate language that would be, in this case, symbolic, and you're thinking with that symbolic language. So again, big debate on this stuff. In the literature for mental imagery, one of the things that appears again and again and again is these linear timing effects. So based upon some, say for example, in this case, if you have an experiment where individuals are supposed to look at some reference image on this left pane here and determine whether the thing that's shown to them is the same as this thing over here under rotation, or if it's different under rotation, depending upon how far the image is on the right pane rotated, there's a linear timing effect that appears with the angle of rotation. So the larger the angle of rotation, the longer the time it takes for people to process this. And so the inference made from this is that people are doing a mental rotation to do this perceptual problem. And you get this again and again. There's other experiments related to scanning a surface mentally that have linear time effects based upon distance, and so forth and so on. So that's one of the nice, robust chronometric findings that you'll have in the literature. And this is something that you'd want to replicate in experiments. Okay, so put on the brakes. So all of that stuff, so it's great, mental imagery, it fuels all this debate about the representational, what's the nature of mental representations that we use and all of these things. Well, there's this phenomena that affects between 0.5 and 3% of the population called aphantasia. And what this is that there are people that do not report being able to ever become conscious of a mental image, right? They when you ask them about this idea of visualizing something like an apple, they think that when people talk about seeing with the mind's eye, that it's metaphorical, right? And I think there's a lot more attention that's coming to this now, but mental imagery, it happens in a continuum, and it's also modality specific, right? Sometimes people might be very good visualizers when it comes to visual modalities, but maybe they can't hear songs in their head. Stan Franklin actually was one of those. He was not able to hear a song in his head, and it was kind of interesting talking about because he played music, right? He was quite good at playing music. So that's the interesting conundrum of this, is that you have people that say they don't have any experience at all of mental imagery. They have very few, if any, deficits in life, right? So it doesn't seem to impact, even in tasks that are supposed to be requiring mental imagery, these rotation experiments where it's supposed to be that people are mentally rotating. That's the hypothesis. So something is going on here that needs to be explained. How is it that they can do these things without mental imagery? So that's the thing, that's the interesting thing to try to model here, is how can we possibly deal with this? So this surprising effect that very little performance differences between people that are normal imagers and people with aphantasia. They still have these linear increases in response time. What is going on if they don't even have mental imagery that's conscious? Now, there is a few differences that have been noticed, and there's a couple little, you can induce some interesting priming things in people with mental imagery or non-aphantasic normal imagers that do not happen with aphantasics. But detail, that seems like that's one of the things that when they're given a task to do, there's less detail in, say, drawings that are produced by somebody with aphantasia. But overall, really very little in terms of impact from aphantasia. So how do we model it? If you look in the literature, it's still batting around all these different hypotheses. Is it that really there's unconscious mental simulations going on and they're just not aware of it? So there's this term blind imagination, like blind sight, which you might be familiar with. You know, people that actually are able to navigate around a room or pick up objects, and they don't even have a conscious experience of seeing anything, but they can be induced to do that. So that's one possibility, is something like a blind imagination thing. Another thing is, so I talked earlier quickly about this difference between object imagery and spatial imagery. It's possible that imagery really isn't a unified thing, that there's a spatial component to it and there's an object properties component to it. You have to model these two things separately in order to capture aphantasia properly. And then it could be that for whatever reason, there's just the opportunity to use a different cognitive strategy. Maybe these timing effects can be reproduced just fine without a depictive representation. Maybe something that is propositional works just fine, and they're just using a different cognitive strategy. And if you look at the literature, there's evidence for and against all of these different things, right? So this is the opportunity. This is where I think cognitive architectures can come in. Can we build systems that demonstrate these different mechanisms? Can we see if they work? Can we see if they don't work? And can we see if we can generalize from them and test some things off of each one of these different possibilities? So this is kind of what I'm interested in, is trying these possibilities. Now, I'm going to quickly go over, I'm sort of running out of time, 40 minutes in, right? Go good? Okay, cool. So in general, there's a bigger question with this, though. So if 97% of the population are normal imagers and 3% of the population are aphantasics, when we build our cognitive architecture, do we do it for everybody? Or do we do it for a certain typical individual? Should we try to do all of it? I'm of the opinion that we should try to do all of it, right? Again, I'm sort of this expansive view, and actually, in some respects, that might even be beyond what Stan Franklin was thinking. I think he was thinking when it comes to really, so medical conditions or other things like that, maybe we should avoid trying to put that into the cognitive architecture. But I think we should try to at least understand what is different and see if we can model it with that base stuff. So I'm sort of the opinion we should do everything. But can we actually do this? Can we actually accommodate both normal imaginers and aphantasics within a single cognitive architecture? And I'm optimistic that yes, if it might be a change in one process that would be active in a normal imager but not in a aphantasic, a change in a property like decay rates, in a preconscious buffer, things like that. So this is what I would like to see happen, is that we can actually understand and accommodate both. And then there's this bigger question of, what is the significance towards this mental representation debate? The idea that people can seem to similarly function perfectly fine without mental images makes you wonder whether some of the support for sort of the depictive, non-symbolic kinds of representations gets eroded a little bit. Okay, so I created an environment. So this environment was inspired by one of Stephen Kozlin's experiments. They called it, so this is a paper, Kozlin et al., 1990. What they were actually doing in that paper, and I showed the diagram earlier, they were showing age effects related to mental imagery, but they described this basic task of trying to understand, or trying to recognize whether something was the same object or whether it was something different. So the environment is using raw pixels, and this is the thing that's actually being compared, is raw pixels. So the one thing that I wanted to do is I wanted to make sure that if I gave this as an experiment to humans, or I gave this as an experiment to software agents, it was basically the same environment. Right? I'm broadcasting the state from the environment. Those pixel images are going out to the agent. It can send actions back in, and then those are processed. And humans are basically doing exactly the same thing. It's the same information. That way I'm sort of trying to control the environment's differences, right? So again, this goes back to the stuff I was saying earlier, trying to prevent any differences that I can. And then I've got an analytics script that's consuming that same broadcast to figure out things like response times and errors and performance overall. So I enhanced the kinds of transformations that were allowed by the environment versus what Stephen Kozlin's experiment did. So rather than just do rotations, this does rotations, translations, and zooming in and out, just to see what the differences are. And one of the things I'm particularly interested in is that, a lot of us talk about, human-like agents, trying to get human-like systems, things like that. So if we were to use this kind of environment and use it against, say, a reinforcement learning algorithm, what kind of behaviors would manifest? What kind of response times would manifest from this? So I think that sort of leads to some interesting things with, okay, well, what about different shapes? Rather than just these reflections of the same shape, what about completely different shapes? How would a typical algorithm do versus an agent that's built with our cognitive architectures? And then the environment will give a feedback signal about whether it's correct or incorrect. Okay, so now going into the implementation I've been working on. So like I was saying earlier about control structures and trying to drive these from a theory, well, all of us are kind of doing that, right? So my theory is LIDA. And so this is the LIDA cognitive architecture. I'm not going to go into all the details because that would take the rest of the presentation at least, but it should kind of be recognizable in terms of the kind of diagrams that you typically see with cognitive architectures. You've got a bunch of short-term memory modules, long-term memory modules, and you have this cognitive cycle that's sort of implicit here. So I said earlier that LIDA implements the global workspace theory of consciousness, and that's sort of present here. This is a global conscious broadcast. But LIDA, in some respects, is a theory of theories. A lot of different theories have been incorporated into LIDA. So global workspace theory is just one of them. Constructivist learning, Piaget's constructivist learning, which is enhanced by Drescher. Barcelow's perceptual symbol systems, two streams hypothesis, all these different things are incorporated. From my work, though, these three are the most important. And so a lot of my implementation is focused on that. Okay, so one of the things, so if you look at this earlier diagram, there is no loop that appears here. This was something that was talked about for a while in the literature, but it was never formalized. So the first thing I needed to do, because I needed mental imagery, mental simulations. So now I have this inner loop where you can think, rather than acting directly on the environment, you can act on an internal environment. And so this is not certainly the first cognitive architecture that does this kind of thing. When I was doing a comparison in my earlier work, I was looking at some of the stuff that SOAR has done, where there's a little bit of a internal action process with some controllers that will fulfill those. This is not entirely different. One of the things that's interesting about it, though, is action selection has the task of figuring out, do we go internal or do we go external in our selected behavior? And then we have special processes called structure building codelets that fulfill that. So this is a minimal version of LIDA. There's a lot of modules that are removed just to focus on the things that matter most for this loop because it's complicated enough. That said, I think I'm going to need a spatial memory module here eventually. But right now, this is basically the focus of it. So at the beginning of the LIDA cognitive cycle, you have sensory memory, which receives sensory stimuli from the environment. So in this experiment, you're getting basically those images from the environment. So you're getting broadcast 2 images of 128 by 128 pixels that goes over into sensory memory. And sensory memory has the task of the first low-level processing of that. So in my implementation, I'm using, this is where my connectionist architecture starts coming in. And so again, the whole task of mental imagery requires the creation of something that was sensory-like. So I'm using beta variational autoencoders, which is a connectionist architecture that you can sort of split in half into a generative portion and a recognition portion. And this is what's actually being used to activate my recognition module. So over here, so this is where there's a handoff between connectionism and symbolic representations. So this is referred to as activation graph. And so you have these nodes down here that receive activation directly from sensory memory, and that activation then spreads across nodes over in PAM. And so this is another one of the sort of the changes that have been made in the work is modal and amodal nodes. So this is, again, part of that hybrid architecture where amodal, going to Barcelow's terminology, is something that is symbolic. It's not directly, we say, grounded. It's grounded through other things. And so those amodal nodes, those are the things that bear the resemblance characteristics from the environment. And there's different styles of associations that can happen in that graph too. The simulator structure building codelet, simulators in quotes here because that also borrows from Lawrence Barcelow's work. He talked about simulators as these generative processes that underpin cognition. So our simulator structure building codelets are what will generate our multimodal simulations of whatever that concept is. So you might get some subgraph from PAM, perceptual associative memory, and LIDA, and then you can reconstitute that using the tail end of that beta variational autoencoder. So one of the interesting and important things, and this is, so with beta variational autoencoders overall, when I chose to use that, I was already thinking, okay, so is this going too far into the engineering aspect? What does this give me? Is this just solving a problem, but it has undesirable properties? Well, the architecture that I used for this neural network is based upon convolutional layers. And convolutional layers have a very nice property where, so if you look at rotation here on this second row, it's not completely invariant when it comes to rotation. The more something is rotated, the similarities to these numbers at the top here from 0.54 up to 1, this is the similarity comparison that I'm doing. And you can see that as it gets further and further away from this reference image in the center, it starts getting less and less and less similar. And this is critical because if I'm trying to replicate a timing effect, if I'm expecting a timing effect, if it's a one-shot recognition, we apparently don't do that. So we don't do one-shot, I mean, at least according to what we see in the response times of these mental imagery experiments, something's going on that seems like multiple causative cycles. It seems like we are, the dominant hypothesis that we are doing a mental rotation. So what I'm expecting my architecture to do, my agent to do, is that it needs to do a little bit of mental rotation in order to determine, is this the same thing or is this a different thing? And so this rotation variance is actually kind of useful because I think that humans appear to have that property as well. Now these other ones though, I'm not so sure about. I think that they might be an artifact of this engineering approach. And that worries me a little bit. I don't think with horizontal translation, vertical translation, or scale if you go small enough, maybe. But I worry about this. So this is one of those cases where I'm wondering if engineering, the need to build the system, is undermining my scientific validity, but I'm just not sure. So I've been running into all kinds of, we're making progress, me and my students are making progress on this implementation. We've got a good implementation, I think, of sensory memory. We've been doing nice scaling up with PAM, and we've got the workings of procedural memory working just fine. Supporting spatial imagery. I'm not sure how to do that yet. So if we're talking about object and spatial imagery as distinct things, I need to build spatial maps, and the reconstitution process is going to be considerably harder. I'm not going to be able to use a simple beta variational autoencoder to do this. So I'm still trying to figure that out. But for aphantasia, I've got to figure it out. I think that's a very important property to explore. Combining real and virtual content. So LIDA has a pre-conscious buffer, current situational model, which is sort of the pre-conscious understanding the agent has of its environment. One of the things that we know from the psychological neuroscientific literature is that you can observe priming and interference effects when the same stuff, like if something is similar in your mind, something out in the world, you get faster response times. If there's a difference, if they're discordant, you get different response times. You're using the same real estate in the brain to do this stuff. So if I wanted to do this properly, I need to figure out a good way of combining real and virtual content, imagined and real stuff. And I'm still working on that. And finally, I'm still seeing a few scaling issues. This environment, even though it seems trivial, it has millions of states. And all of those states are images, right? So trying to scale that up in a way that doesn't erode, the architecture itself is tricky. PAM, I think we've got that figured out. Procedural memory, which is based on a modified version of Gary Drescher's work, where you basically are learning a data structure called a scheme for the context, action, and result combinations in the environment. That is a little bit unmanageable right now. So we're trying to figure out how to scale that up. But making progress, but there are definitely some serious challenges still. So one of the things that we also did, and I alluded to this before, we want to see differences between what we're doing and some of the mainstream algorithms. So we used, the same low-level feature detectors we're using for sensory memory, we took that, we hooked it into stable baselines algorithms. So that's some standard reinforcement learning algorithms. We used one called PPO. We also used DQN. And we wanted to see what would happen if we did this. And it was kind of interesting, actually. So it was actually able to get 80% accuracy, which is better than I thought it was going to be able to do, given what it did. Of course, constant response times. There's nothing like a cognitive cycle. It's just a feed-forward neural network. It's going to do that. And we use this reward function. We're penalizing movements, so it wouldn't just do infinite number of movements. And we're giving it a reward for getting things right and a negative reward for getting things wrong. Is there any way you can hit play on the video? Yes. So what we saw is this. So what I expected to see, so I told you earlier that the beta variation autoencoders, the encoder portion of it, it's producing representations that are perceptually variant, meaning that if you have something that's rotated by, say, 45 degrees, it's not going to have a high enough activation to recognize that as the same kind of thing. So I expected to see a little bit of, so in this particular mode of the environment, it's able to actually directly manipulate the objects, because this is supposed to be like a learning setting in the environment. And then there's the test where you can't actually rotate anything or translate anything on the right side. But it never did. It just memorized the patterns on one side and the other, and just answered the things as fast as possible, I think because of this part of the reward function. But that was kind of interesting, but it was surprising to me that it was actually able to get 80% accuracy, not doing any kind of rotations or anything at all to simplify the perceptual task. So it's kind of, it was somewhat counterintuitive to me that actually happened, but it's interesting to think about, and I think, yeah, something to explain later on. So that's really kind of where I'm at. A lot of it is speculative. We're trying to go. Yeah, so any questions related to the work?
Hi. My question is the following. If you go to the philosopher Hegel, he says that there is a difference between imagery in the sense of the images that we are seeing that are just in front of us and images that are created by this imagery process, in the sense that the image that we are seeing are vivid, and those images that we are imaging are faded or blurred or things like that. So do you believe that this could means that the representation of these images that are being generated by imagery, they have a different process, and they are not just represented in terms of matrices or bitmaps or things like that, but they are using some kind of schemas or other kinds of articulating those images and this could be the reason that to rotate a large angle is more or less the same as rotating a small angle. Do you believe that this could be a possible solution for what you're saying?
Right. So it's the first point about the differences in vividness. So when you're scanning somebody's brain in an fMRI under an imagery task versus perceptual task, one of the things that is pretty common is that the degree of activation is less in the imagery task. So I think that is sort of a plausible, neural correlate of less vividness. We're seeing, less activation, but it does, and again, all this is controversial, right? But there does seem to be a fair amount of literature that suggests we are reusing the same kind of canvas. So I think there is, like you said, there's a different process, an imagery generation process, imagery manipulation processes. So those different operations that Stephen Coslin talked about generation, transformation, the maintenance and introspection, there are papers that are written that sort of map each of those individually out. And so there's definitely some other machinery that's going on to induce these images. But to me, even though it's controversial, I feel like it's probably using the same sketchpad because those priming effects and interference effects. I mean, if you can do, whatever transcranial magnetic simulation to kind of interfere with people from doing imagery by, hitting somebody's, primary visual cortex, primary visual cortex, that's fairly, compelling evidence that there's definitely a lot of overlap, and it probably using a similar, neural substrate to do it.
Okay, thank you.
Thank you. Hello. Oh, okay. Okay. What does being aware or conscious mean in the LIDA system? Yes. So LIDA is based on a theory by Bernard Bars called global workspace theory. So there is a module in LIDA called the global workspace, and that's where a competition happens for consciousness. So you have these different data structures called coalitions that compete for consciousness. The one that actually wins that competition, whichever one has the highest activation, is broadcast out to every single module of the system. And so if you wanted to, so there's a lot of different philosophical terms like access consciousness versus phenomenal consciousness and things like that. We don't directly try to model phenomenal consciousness or what it feels like to have that subjective experience in LIDA. What we do, though, is deal with the information bottleneck and the availability of content. So when something is conscious, it means that content is considered important to the system and everything should receive it. And that's also the learning signal in LIDA too.
Okay.
Some other questions? Yes. No.
Hello. So you may have thought about this, but when you were talking about the spatial imagery and like the challenges, have you looked into, you probably have, but just bear with me, the literature on like different cells that basically build spatial maps. And a lot of that work, it basically kind of translates into what you see with like game development. And so the representations of the things in the environment are kind of abstracted away in these maps.
Is this like the cognitive maps that you
Yeah,
see? With
like place with the Mosers did the place cells, grid cells.
Absolutely.
So,
yeah, exactly.
Yeah. So have you thought about maybe using that kind of angle to get around some of these challenges?
So in LIDA, we have already done some work related to modeling place cells and
Awesome.
things like that. The trick, though, is that it was always used for navigation tasks where it was like an overall environment and the locations, so little nodes. What I need to do is something like have different nodes for different salient parts of objects. and then reconstitute each one of those different parts, because we know that there's like this serial regeneration. Like you don't regenerate everything all at once when it's complex. If it's a multi-part image, there's another timing effect related to the parts. You do one part and another part, and another part, another part, based upon like where you introspect. So I think you're on the right track. That's kind of what needs to be done. But from an implementation perspective, so I could generate each part, but I've got to then integrate it together.
Right.
And so there's another process of integration that needs to be done with those parts to make sure that they make sense together.
Right. So thank
But
you.
yeah, it's great.
Someone else? Okay.
Good morning. Thank you for the talk. I would like to make some comments about what you present. One is, the first one is to say that what you see is an illusion. It's not really a reality. It's a reality created by your processing centers of vision
Like the predictive
from the
processes.
data taken from your retina. Your retina produces something like 1,025,000 of signals. Then they are processed by the retina and sent through the optical nerve 1 million of communication channels. Each channels goes to different region of the brain. One is process the shapes, one process the shadows, and the other process colors. So when you see this kind of problems, fantasia or whatever, is because your memory is not properly keeping the data as they were produced. They miss some of the data. And when you try to reproduce and pass through the same processing system, they produce a different shape.
There's a dynamic aspect to every recreation of
Yeah.
an image. Yep.
Yeah. So some people have no access to shapes and colors, just to the shape, to the shape and colors, just to the shape is why they can reproduce only those things. Some others has the ability to access the shapes and also the shades, and you see this image is colorless, and other people can take all the information, processing again, and reproduce exactly. And this is why they are the artists, the painters. They have that in mind, because they can see the picture once and then reproduce exactly in a canvas.
One of the things that's amazing with the aphantasics is that some of them are artists, even though they don't seem to be able to actually conjure up images, consciously anyway. They're able to reproduce beautiful works on canvas. So going to what you're saying, though, there is different properties that need to be combined together. And it seems like, so there's one of the things I'd mentioned was like this spatial versus object imagery, sort of the coordinating frame and then filling in the details. There's a possibility that that aphantasics really have the top level coordinating frame, but they can't go all the way down to all those different properties of the fine details of the objects. So that's definitely one of the hypotheses that's out there, is that there's partial reconstitution, but some would say that there's no reconstitution. But then how do you explain the timing effects?
Bring the image. The image processed is again stored, and if your process system lose some information, when you restore the new information, it will miss more and more and more.
So you're saying on the storage side, it might be one of the, and absolutely, that makes perfect sense. Even in the implementation I'm doing, you're building a compact representation, and then that compact representation has to be reconstituted. And so if that is not done properly, like if you're not able to extract off those salient properties at the encoding time, yeah, you're out of luck. You're not going to be able to reconstitute it. So I think that's another opportunity for modeling some of this stuff as well, is maybe in the encoding side, you're just not, you know, what's being encoded, is it insufficient? Thanks.
Thank you. Another question? Okay. Will be here in the next day, so if anyone has some question for him, take your time. Okay, this is a pleasure.
Pleasure's all mine. It's great to be here.
And hear your response.
Thank you. Thank you, Felix.
Thank you.
sharing this session. Next is the time for my college Charlie, Juan Carlos. Each speaker have 15 minutes to presentation and 5 minutes to question and discussion. Okay, please be careful with the time, but our schedule complete. Okay, and thank you, Charlie, and have 15 minutes. Okay.
Thank you so much. Well, let's begin with this presentation. I'm glad to here with you in this 60th edition of BICA 2025 at Puerto Vallarta. My name is Carlos Zárate, and I'm here to share with you a work that we are recently started to study that is titled Self-Structured Data Representations for Multimodal Systems, an approach based on adaptive competitive dynamics. So let's start with this presentation. This is the content that we are following. Let's start defining what is the multisensory processing. This term stands for the influence of a sensory modality as the visual or the auditory over the activity of another modality. Using this joint information, it is possible to generate some inferences that are partially implied in each modality that you're using to generate this inference. So, may click on the Victor, please. May click on this to the right, full to the right. Thank you. Click. Okay, thank you. As a practical example, we can perceive an image. You see, for example, this dog, and you say, okay, I'm sure that this is a dog, and followed by its barking, no? Okay, so you have this relationship between the sound of the barking and the image of the dog. So internally, you have an internal representation of both stimuli. So you can say effectively it's a dog. But what happens when some of these stimuli are confused or ambiguous? You have a lack of information. So maybe you can confuse a muffin with a little dog. and you can say, well, I guess this is a dog, I guess. But this stimuli is followed by a sound that clearly is not a bark. So the internal representation have a conflict, and maybe you can say, well, perhaps it is not a dog. This is the basic intuition. So for the analysis of the state of the art, we have defined a criteria within the literature review that are applied for many of the algorithms and techniques that are commonly used within the multimodal processing problem. For example, we have the interpretability, which responds to the question for, is it possible to know what the model is learning? Or the log complexity, does the model implementation is a technical challenge? Adaptability for, does the model can handle data changes, anomalies, noise, data alterations by a test change? The scalability for, is it a difficult task to increase the model size or decrease the model size even? And the last one is the traceability. For, is it possible to know what is the knowledge used by the model to provide the responses? And this one is important for example, privacy context. This is a general review for these algorithms like CNNs, transformers, CSA kernels, VAS, GANs, and we can see that there are some criteria that are not completely covered by some of these algorithms and techniques. The conclusion is that, for example, the adaptability is available and handled by in general by the several models. The scalability, well, it not seems like considered as a strong decision for design for these algorithms. We have that the implementation complexity and interpretability, well, are traits that can be improved to make these algorithms and techniques more accessible. And finally, we have the traceability for most of these approaches. It's not a strong design decision, and we consider that this inclusion could provide, well, more capabilities for these algorithms. For example, in the context of data government, as I said before, for the privacy of the user data. So the problem statement for this research is that the integration of multiple heterogeneous information sources implies to deal with, of course, different data structures. I mean, vectors, matrices, for example, features correlation, as well as time alignment issues like asynchronic data. This motivates several of these models, the using of techniques that could turn it on large and complex implementations. Such models require, well, high computational costs and training resources to generate the inferences we need to work with. Likewise, there are methodologies with a black box nature, which implies that the models we build with that methodologies have a low interpretability, as well as the requirement of large data sets with minimal quality. And this is an important field to study because it has a lot of application areas. For example, like the healthcare and medical support, virtual and augmented reality, and of course, the development of robotics and better human-machine interfaces. We have based our work and neuroscience literature, for example, studying how the cerebral cortex of many mammalian species shows this topographical organization with neural assemblies representing similar sensory inputs. An example of this effect is the so-called cortical homunculus, when you can see that there are some of parts of the body distribute along of the motor cortex and sensory cortex, when we can see that there are some parts of the body that have a bigger portion of the cortex. This depends of the functional importance of these regions. And these maps are not static structures. In fact, they are dynamically organized. And of course, within the computational support, we have an equivalent or a base algorithm. The well-known self-organized maps proposed by Conan in 1982. It's a technique of some unsupervised learning to generate a low-dimensional representation of the data input. This approach uses competitive learning, where you have, for example, a neuron, and you can take an input and say, okay, what is the neuron, which vector is similarly to the input? And you can say, okay, this is the neuron that has a similar vector to the input, and so this neuron is the winner. It has the data nearest to the input, so this neuron gets activated and receives an adaptation. We're using this sample approach to develop and study the possibility of implement a model to solve or contribute to solve the multimodal processing. Here's a general view of the model that we are proposing. So let's start talking about the S structures that we name as assemblies. The assemblies are structures that we are using to hold these storage units. These storage units are used to store and search some patterns within the data we're using as input. So when you take, for example, a sound and the auditory says, okay, I guess this unit has the best match for this data, so we're using the response provided by this unit. Same case for example, the visual assembly. Now, the next structure is the modality mixer that take these responses and build representations based on concurrent data. For example, we can execute the model many times and take, for example, this unit, this auditory unit and this visual unit, and put it within this multimodal activation buffer. And this process is repeated again and again and again until we fill the buffer. So once the buffer has been filled, we take one of these units and as a reference, and it's quantify the proportion of simultaneous activations with units of another modalities. It's, I mean, this one with this one with this one, and so on, until we find, well, until we take this quantifications. I'm sorry, and we can use it to build this kind of vector that represents the relationship of simultaneous activations of this unit with other units from other modalities. So this vector is used to update the unit response to learn the relation, of course, of other modalities. Well, the case of study for this model was built by synthetic data, images, and sounds. And we added a noise of 23% of the data, and both modalities were positively correlated by the frequency and the brightness levels. It is to say, as high the frequency of the sound is, as high the brightness level of the image is. The hypothesis is that the design of the model will allow to create representations of the observed data and generate consistent responses that capture information of the relationship between concurrent stimuli. So as you could see in the previous slides, the model could make the following representations for the auditory and the visual data, where the auditory units got distributed along the frequency axis. As you can see, this unit represents the lower frequencies of the sounds, the low mids, the high mids, and the high frequencies. And the visual units got distributed along the brightness axis, where this unit represents the lower brightness images, then the low brightness, a little higher brightness, and the higher brightness. Well, the higher brightness, I guess. So we got some observations about the responses produced by the units, where we have two cases. The high cross-modal consistency, when this unit got activated simultaneously with this unit, when we can see that this unit is highly correlated with this other unit, and the same case for this other unit. So we can say that both are commonly activated simultaneously. But the other case is when this unit got activated with this other unit, but they aren't correlated. Okay, I mean, they didn't get activated simultaneously in the past. We consider that this kind of representation is very useful to the units, can be projected into a reference frame in an easy way. You can take, for example, the visual units as an axis of this frame. Okay, thanks. And take the projection, the response of this auditory unit and project it as a vector within this reference frames. So you can project any other units from any other modalities and compare them and perform, for example, operations like the distance measurement, transformations to determine relationships between vectors projected into this reference frame. So given that the responses are linked, are strongly linked to the units or reference of a response, can be used to identify, for example, this unit, and therefore assume the kind of data that can produce this activation. In this case, images with a low level of brightness. The conclusion is that we are proposed a biological inspired model for structured data representations for multimodal systems. It can identify, store, and learn in an unsupervised way some patterns in the data. Of course, the validation shows that it has an ability to learn from noisy inputs without requiring a large level of data sets. But it has some limitations, for example, include the lack of testing in real-world data, scalability changes, and the need to integrate more complex cognitive processes. So the criteria assessment that we we have applied for the other algorithms and techniques is for this model, as you can see in this slide. The main problem is the scalability, because we have not defined a role or protocol or any process that we can use to stack, for example, an assembly with an assembly, or add more units without any consequence. There are some references used, and thank you for your attention.
Okay, thank you, Carlos. Does anyone have any question? Okay.
Hi. When you have these two sense modalities, and there is some time delay in the sense that every time something happens, for example, in one modality, after, let's say, a few seconds later, it happens on the second modality, could you still correlate them, or they need to be exactly at the same time to be correlated?
Okay, we're considering that the collected stimuli has at least generated within a window of 100 milliseconds. I guess that it is the standard window considered for the human's basic stimuli perception. So that's the assumption that we're making for this work.
Okay, thank you.
Thank you, Doctor.
Hi, thank you for your presentation. Can you go back to slide, I think it was 58, and about where you stated the some of the limitations of the work?
Victor?
Do-
Make click on the slide, please.
I mean, well, anyway, you said that scalability was one of them, right?
Okay, according to the scalability.
Scalability. Is it in terms of the being able to do the real-time processing, or is it in terms of the number of signals that you can process? So can you be a little bit more specific for the scalability?
Okay, the scalability problem, it has multiple issues, because yes, we can talk about the real-time response of the model, because if the assemblies has too many units to search a pattern to match, well, the model takes a long time to make a response. But okay, no, it's here. Okay. Well, yeah, it refers in part for the real-time responses, and also for increase the model. I mean, you can add so many units, but the assembly does not assure that it will use all of these units to increase the representation.
I mean, especially if you think about the like the number of signals that were mentioned before, like there are thousands of signals for the retina and so on, and things like that.
Well, we are assuming that we are receiving inputs from, for example, a camera, because we're not limiting the definition of a modality as, for example, biological vision. We're assuming that as a sensor, for example, an infrared sensor, could be perfectly a modality within an intelligent system.
Okay. Thank you.
Okay, that is all. Thank you, Carlos.
The next talk is online, remotely. Is Nasrin Mokarem. He will join us from Netherlands. Okay, and Nasrin, are you?
Yes, can you guys hear me?
Okay. You have 15 minutes, okay? Okay.
Hi everyone, my name is Steven Lopadem, and I'll present my research on enhancing cybersecurity through adaptive networks and AI coaching. I'm currently not doing very well at the 60 days, but I will still try my best to give a good and clear presentation. This research explores improving cybersecurity not technically, but also by supporting how people think, learn, and collaborate under pressure. And there's a lot of ground to cover and only a limited time, so I'll dive straight into the material. I began the research by studying two real-world cybersecurity incidents. The first one was Operation Triangulation, where attackers exploited Twitter-code iMessages to remotely hack iPhones. And the second one was the Destroyer attack, where Ukraine's power grid was targeted by using outdated ICS protocols, which caused physical disruption. And both of these examples involve scenarios I use later on. Next, I focused on the human aspect. I looked into mental models, how individuals understand and respond to threats. Accurate models can lead to effective actions, and inaccuracies can lead to mistakes. Shared mental models are crucial for cybersecurity teams to collaborate efficiently, share roles clearly, and reduce errors. And then I looked into two different kinds of learning: organizational learning and social learning. Organizational learning is systematically capturing lessons from incidents to improve future responses, while social learning is learning by observing others, and this can be very effective but also risky if bad practices spread. And these concepts, they set the stage for my research. Cybersecurity is equally about human cognition and teamwork. I created 4 different scenarios, each with its own corresponding network model. And while each scenario presents a unique narrative, they all center around collaboration within a cybersecurity team. So like I said, I used a network-oriented modeling approach, which means I represent cognitive and organizational processes as a network of connected states. Each node in a network is a state, like belief, an action, an observation, and there are arrows between those states, and they represent causal influence. And these influences evolve over time, so we can simulate how people adapt, learn, or respond to cybersecurity incidents dynamically. Scenario 1 depicts the employee's regular routine at a hypothetical smart energy company. The company faces challenges such as outdated ICS protocols and zero-day vulnerabilities in their iOS devices. And as part of their daily responsibilities, the employee performs various tasks. And if any issues are detected during these checks, the employee contacts the advisor, and the advisor serves as a team lead for guidance. And based on the advisor's input, the employee may then take corrective action. And looking at the network model, we see that it only includes the base level. It's the pink level that you can see. And this is because no additional layers are needed. All the team members, they possess perfect mental models, so there's no need for learning or adaptation. The model contains 2 mental models, one for the employee labeled E and one for the advisor labeled A. And both agents, they carry out specific actions in the world. So to represent this, the model includes action ownership states, which determine who initiates which actions based on their internal reasoning. There are also contextual factors in the model. There are different types of connections between states. We have black arrows, and they represent links between states within the world or within mental models. We have blue arrows, and those show connections between ownership states and either world states or mental model states. We have orange arrows. Those represent observation links. So it captures how the employee and the advisor perceive events in the world. And there are also gray arrows, and those come from the contextual factors. When we look at scenario 2, it begins when the employee unintentionally modifies a firewall setting without proper security review. And this is a problem, so it causes operational disruptions. And in response, the employee contacts the advisor for immediate assistance, and this marks the start of this scenario. And one of the contextual factors in this model reflects the advisor's prior experience with similar issues. They have encountered a wide range of comparable incidents in the past, and the advisor's responsibilities now include reviewing firewall changes, assessing modifications, and most importantly, clearly explaining both the problem and the solution to the employee so that the employee can implement the fix. The network model for this scenario again only includes the base level since both agents still have perfect mental models, so no extra layers are needed. And also, as in scenario 1, the model includes 2 mental models, and we again see the same type of arrows. Now we go to scenario 3, and this builds upon scenario 2. And here there's a change in team dynamics. The advisor falls ill and only completes the first 2 tasks. The remaining responsibilities, which are interpreting the results and explaining the issue to the employee, are now passed on to a consultant. And this consultant leads a different cybersecurity team and is unfamiliar with specific protocols used here, which makes the consultant feel insecure and stressed. And this network model includes 2 higher order adaptation levels. So you see the blue and the purple levels, because in this case, the mental models are no longer perfect and adaptation plays a role. There's now a 3rd mental model for the consultant, and you can see on the 1st order adaptation level different adaptation processes. And if we look at one of them, for example, for the employee, one key adaptation is between the eternal state E4, which stands for assessment shows misconfigurations, and E6, which means consultant explains problem and solution. And this is modeled by a self-weight W. And then you see a red adaptation arrow reinforcing the expectation based on experience. And there are similar adaptation links for the advisor and the consultant. Additionally, you can see the weight state WE6C6, which captures how the employee state activates and reinforces the consultant's corresponding mental state. And this reflects social learning. On the 2nd order level, we can see MW states, and these dynamically regulate the persistent factor. So it controls how strongly past experiences are retained depending on the context. And under stress, as in this scenario, the MW values they drop, representing reduced retention and impaired learning. Scenario 4 builds on scenario 3, but introduces an AI coach. And this AI coach has perfect knowledge and is fully aware of the specific protocols and procedures used by each cybersecurity team. So in the organization, every team has its own virtual AI coach tailored to its internal processes. And the AI coach supports the team in 2 ways, by contributing to organizational learning and by actively monitoring each step of the procedure. And when something goes wrong, it will signal something. And in the network model, this is reflected by the inclusion of an extra mental model, one for the AI coach. And as you can see, unlike the human agents, the AI coach doesn't have ownership states because it doesn't perform actions in the real world. Instead, it provides guidance by observing and giving feedback when necessary. And this is shown by the observation arrows from each world state to the AI coach mental model. And at the 1st order adaptation level, we see the weight state WAI4 AI6, which connects to all other learning related weight states. And this shows how the AI coach injects its knowledge into the team's learning processes. There are also 2 new states introduced, MS6 and DS6, which are the monitoring state and the decision state. And the decision state, it represents the AI coach decision-making process about whether to intervene. If WS6, which is the world state representing the successful execution of step 6, is activated as expected, the decision state is weakened, meaning there's no intervention needed. However, if the world state is missing or not progressing as intended, the decision state activates, prompting the AI coach to communicate with the human actors. And this communication is modeled with the communication state in the 2nd order. This communication then influences learning at the 1st order level, as it leads to adaptations in the W states. So it shows how, like, the AI coach's intervention helps reinforce or correct the team's internal expectations and behavior. If we look at the result of scenario 1, we see that everything is progressing as intended. The employee starts with a network scan because you see the world state 1 rising, and it reviews vulnerabilities because you see WS3 increasing and WS2, meaning that there's no problem, it stays at 0. So there's a problem. But as you can see, all other world states are happening. So the employee continues their diagnostic steps. And although the advisor begins offering guidance early on, because you see the world state 15 rising around TS2, the employee doesn't act immediately. Instead, they complete all checks before initiating actions. And this shows a structured step-by-step approach where the employee relies on advisor input but waits for a full diagnostic picture before taking corrective action. In scenario 2, we again see the progression of the world states, but now in the case where the employee made unauthorized firewall changes. And it starts with the employee contacting the advisor. You see WS1 increasing. Then the next world states happen again. But you can see that everything is going well because WS8, meaning the solution is working, is increasing all the way to value of 1, while WS9 is going down because you first see that they are both rising at the same time. But when WS7 is nearing completion, and W7 stands for the implementation is almost done, you see WS9 dropping, meaning that there's a success. So this figure shows also a smooth resolution process, again enabled by perfect mental models and clear communication between the employee and advisor. So the first two results I showed, you can see that when there are perfect mental models, even when there is a mistake, eventually the implementation succeeds. But for scenario 3, we have to look at 2 different figures because here we can see a difference. The first figure focuses on the world state 6, meaning the consultant explains the solution to the employee. And the second one will provide a full overview of all world states. Here we can see that W6, it never occurs because the consultant who takes over from the unwell advisor struggles under pressure. So the learning state of the consultant, the orange line, it has a slight decline due to forgetfulness and only reaches a value of 0.5 due to stress. And as a result, the consultant's mental model and the ownership state only show a weak temporary activation. So WS6 remains inactive. So the explanation of the problem and the solution to the employee never happens. When you look at the next figure, we see the broader impact. The process again starts with WS1. But if you look further, we see a very big gap between TS 1.9 and 4.8. And this is because world state 6 is missing due to the consultant's inability to act. Because the consultant couldn't retain enough information to be able to perform its task, which was to explain the problem and solution to the employee. So eventually we do see the world state 7 happening, as the employee implements a solution alone. However, we see WS9 spiking to 1 and WS8, meaning that the solution would have worked, it remains at 0. So this confirms that there is a failure. So in short, this scenario shows how imperfect mental models and stress disrupt collaboration. So unlike scenario 2, the absence of shared understanding leads to poor outcomes. For scenario 4, we again look at 2 different figures. In the first figure, we see the world state 6 now successfully occurring. So unlike scenario 3, the consultant's learning curve, it steadily increases without decline, and it quickly reaches a value of 0.9. So this means that there's a strong knowledge retention. And this improvement is due to the AI coach. We see the purple line, and this provides perfect team-specific knowledge. And as a result, the consultant's mental model reaches full activation, enabling ownership state and the successful explanation of the issue. The AI coach also prepares to give feedback. You see the communication state CS6 increasing, but as the world state is progressing correctly, the need fades, and you see it also again dropping to 0. And the second figure confirms the overall success. We see everything going as intended, but the most important part is when you see WS8 rising, indicating that the solution is working, while WS9, meaning that there's a failure, still stays at 0 throughout the process. So overall, this scenario shows that even now, without perfect mental models from the human team members, the presence of an AI coach with perfect knowledge ensures smooth and accurate execution. So achieving success where scenario 3 failed. I also ran a what-if analysis using 3 if factors. And for the first if factor, I looked at how much the AI coach shares knowledge to others. So normally the AI coach shares its full knowledge, but I tested 3 different cases: low sharing, medium sharing, and high sharing. And the second if factor is knowledge sharing between team members, and this checks whether the consultant or the employee and the advisor help each other learn. Cybersecurity teams often work independently, but they may still share quick tips or help when needed. So I tested 2 cases, no sharing and some sharing. And the third factor is the consultant's attention. So this factor checks whether the consultant is paying attention during the implementation, and I tested no attention and full attention. And to measure risk, I used 4 what factors. The learning of the employee being low at TS2 and TS14, and learning of the consultant being low at TS2 and TS14. And I specifically looked at these key people because they are most important in the procedure. The consultant explains the issue and solution, and the employee applies the fix. And I measured their learning at these specific times because at TS2, I could ask the question, did they start learning it early enough? And at TS14, I could check if they retained enough knowledge to do their job. And as you can see, the first if factor, I needed a representative average. So I used different probability distributions to reflect how frequently each level might occur. For the low level, a left skewed beta distribution was used to simulate rare and minimal sharing. The medium level was modeled with a uniform distribution where all values are in a range equally likely. And the high level was modeled with the right skewed beta distribution, which then generated values close to 1, because I wanted to reflect strong and consistent sharing. And this analysis showed that when the AI coach shares little knowledge, colleague interaction is absent, and the consultant is inattentive, learning fails at both early and later stages. And even with an engaged consultant and colleague support, low AI input still leads to poor outcomes. So human factors alone cannot compensate for an uninformative AI. With medium AI sharing, learning only improves slightly. Even with an attentive consultant and colleague collaboration, retention at TS14 remains below the safe threshold. Hi. Yeah, I will go straight to the conclusion. Thank you. So what we've seen is that through adaptive network models, you can simulate different team situations, and adding an AI coach helps fill in those gaps, and it supports better learning and communication. So overall, an AI coach can be a powerful tool to support human thinking and strengthen cybersecurity from a cognitive perspective. Yes, so in the future, it could be tested with real-world data, and it's also interesting to see how multiple AI coaches could be connected. But for now, the results show that modeling paired with like thoughtful AI support can really strengthen cybersecurity responses, not just technically, but also cognitively. Thank you. Yes. Y- Yes, so like you said, indeed. So this is a formative model, right? It's designed to explore currently how human cognition, stress, or different things can interact during cybersecurity incidents. So while they are hypothetical right now, they are grounded in real world cases. So if I think about validation, I would think about comparing simulation outputs to real team behavior. So using stress indicators or team communication logs, and then implement that in my model um, to analyze the model's behavior. So this phase right now isn't about prediction; it's about understanding the mechanisms. But later on, I would want to integrate the real world data. Yes.
behavior of collective of peaceful agents in the presence of strong predator agent. The work considers a model of competitive interaction between sufficiently large group of relatively weak peaceful agent and strong predator agents. The main goal of the work is to analyze ability of weak agents to suppress the predatory agent. The predatory agent can attack the peaceful agent, kill and eat them. The model will analyze by means of computer simulation. Related works. The most closed work was the model by Burtzler-Tuchin. It is reference once. This model studied a rather complex model of evolutionist self-organization, and it is in particular, in some cases, the struggle between a group of relatively weak agents and strong agent was observed, similar to the attack of a large flock of starling on a sparrowhawk. The reference to Conrad Lorenz. The approach, we consider the world in which peaceful agent and predator agent are located. This world is one-dimensional chain on n cells. In each cell can contain several agents. Some cells contain portion of food of peaceful agents. Each agent has its own resource. When a peaceful eats a portion of food, the resource of this agent increases. At other actions, the resource of this such agent decreases. If the resource of any agent in the process of evolution become below zero, then such agent dies. Peaceful agent can perform the following action: resting, eating, moving to neighboring cells, reproducing, moving from predatory agent, and threatening the predator agents and attacking the predator agents. The predator's actions are moving from threatening peaceful agents, attacking the peaceful agent, intending to kill and eat it, and resting. When the predator kills a peaceful agent, the predator agent eats it. In this case, the predator resource increases significantly. During the simulation, the dynamic of agent resources was determined in figure 1. This figure shows the dependence of R large, the dependence of resource of predatory agents are large, and average resource of peaceful agents, average in population. This figure shows that after short initial period, the resources of peaceful agents increases. Analysis of simulations results that at initial moment of time, peaceful agents often die, and the predator eats them. Due to such process, the predator's resource increases initially. Later, the predator resource decreases and decreases to zero, and predator dies. That is, in this case, relatively weak peaceful agents suppresses the strong predator. The fold size was N50 cells. The number of cells with a portion of food was M is equal 25. Additionally, we analyze the situations with smaller number of food portions for peaceful agents. At 20 piece at 20 piece food portions of food, the results are only slightly change as compared to figure 1. But at m is equal 10, the dynamic change radically. The predator mainly survived. The resource of pill food agent decreases significantly. In this case, the peaceful agent will suppressed. That is, this small amount of food, for peaceful agents, the strong predatory agent suppress weak peaceful agent. The conclusion. It was shown that a collective of peaceful agents, rather large collective, is capable to suppress the strong predatory agent. The peaceful agents need a sufficiently large amount of food to ensure their ability to defend themselves. This small amount of food for peaceful agent, the predator agent suppresses peaceful agents. That's all. Thank you for attention.
Thank you, Mr. Vladimir. Any questions? No? Okay. We continue with the next.
Excuse me once more for technical problems.
Don't worry about that.
Yeah, thank you so much. So let's continue with the next speaker, Omid Madani. Are you ready for to present?
Hi. Yes, I am. I can't share yet. So
Okay.
send request for sharing, and then now I can share. And here it is. You can see it probably. And let me play it. Okay. It's good?
Okay, we can see you.
Okay, great. So I'll start. Again, thank you all. Thank you to the organizers. I'm Omid Madani. This is joint work with Brian Burns and Reza Akhbali and Tom Dean. It's work on agents, single agent. It would be nice to make it multiple agent and with no actions and so on. But yeah, it's a single agent. The question is how does memory help, especially and learning and planning, all kinds of strategies in a changing world. The key point is in a changing, uncertain world. And I'm sorry, I might have technical issues too, because I've noticed that my Zoom is unstable, gets broken, and then I come back like in 20-30 seconds. So bear with me if this happens during the talk. Okay, so let's go on. So if any actionable item you want to take from this talk is to check out this video of squirrels learning to navigate a maze that was set up in a backyard. It's a great video. Ninja Warrior, search on Ninja Warrior backyard squirrel. So in biological world, I think there's still a lot of intelligence that we cannot build. So, and this code is definitely apt, I think, just as a general life advice. Let me try to kill my unmute video. I don't know how to stop video. Okay, so yes, so and the last part of that the author says that it takes courage to move on, knowing that what you know might be incomplete and even downright misleading takes courage. Definitely applies to our work. So it's by Robert Jordan, Winter's Heart. You go on anyway. And portion of wisdom is knowing that what you know might be outright wrong. Okay, so context and motivation. Tom Dean had this vision that we could use several existing AI tools to make an agent that would learn, that would be flexible, had a realistic, limited sensing, perception, and so on, and acquires the skills by doing things, perhaps hierarchical perceptual skills and action skills, and remains flexible. We discussed it and many papers later and many discussions, like a year or so later, we finally decided, okay, this is a good area. So the change, uncertainty, the world is not static, its world is dynamic, right? So deep RL, deep reinforcement learning, model reinforcement learning has been very powerful, but it's sample hungry. So if your problem is static and you have lots of data, great. But again, the real world is productive and not going to wait for you. So non-stationary and open-ended, what should we do? I don't think the existing techniques can handle that. On the other hand, there's a lot of discussion in the cognitive psychology, cognitive science, neuroscience, about map-based versus path-based, egocentric, allocentric, and so on, and the role of memory in all that. So also innateness and bias of algorithms. Picture the giraffe, baby calf, just after a few moments after being born, learns how to stand upright. That's amazing, right? It's probably innate, right? It's probably hardwired. So we shouldn't shy away from hardwiring things, but learning should be a big part of the work too. So anyway, we converge to this simple task, at least a starter problem, right? Two-dimensional grid world. Your black is you can navigate. The agent is the blob, the circle, the blue circle in the middle. That's its home base in the middle, and it has to get to food. And there are barriers. There are these barriers that it can't go through, so it has to go around them. And you can't go off the grid either, and it has to find a path to food. It doesn't know where the food is, and that's the thing. So 4 actions, left, right, 1 adjacent cell to 1 adjacent cell, up, down. No orientation, that can cause. Time is discrete and increments with action execution. Unlike the previous talk, it would be great to extend this to when you don't do anything and the world might still change and you can rest, right? But yeah, in here, you have to do it's 1 agent on action. Observe within the radius of 1, 2, just like actions of 1 point. And we can use path integration. The agent can use path integration, which is very simple. Location XY is incremented appropriately. Let's add 1 or -1. The agent can do that to keep track of where it is. It's home base, it's assumed it's 0, 0. So that's kind of hardwired. But there is motion noise. We have a knob on that. So pictorially, this is it. 4 basic actions for the agent to the adjacent. It can go diagonally. So if there are barriers, it can be less than 4 actions. And the agent knows, the environment tells it what this is another assumption, right? The agent knows what the possible actions are. At least most of our strategies have that. And motion noise, so again, the knob for that. The agent intending to move right can move left with some problem, or stay the same, or might hop 2 points if there's no barrier. There are 2 cells forward, or go up. Or again, this we have a knob. Some percentage of time it might do that, and that percentage could be 0, no motion noise, or it could be. And we mentioned that it has a sensing radius 1. So the 4 adjacent cells, it can see where is the barrier, where is food, and so on. So routes to food, the agent's task is daily, get to food. And once it gets to food, the problem restarts. Next day restarts. Next day begins. Okay. There's another problem about how does it go back to home base, but we think our strategies, we're going to say that map base helps this. And you can easily change the source and destination. But so we just looked at the problem of every day. Agent wakes up, needs to go to the food. First day, it doesn't know where food is. Subsequent days, food may change too, but most of these experiments, the barriers change from one day to next. Okay, and so that was one path to the goal. If there's a barrier, there's some, or there could be other paths too, right? That was a pretty good pass, the first pass that you saw, but usually it wastes time, right? The agent doesn't have a full view. It's partially observable, it just sees the neighboring. So general goals, first question is really memory and planning, making a map and those things, can it be done under change? How much change? When is it useful? How much can we change the barriers every day and still, because planning memory takes a lot of infrastructure, a lot of computing machinery. So can a learning agent be fast enough? Yes, map has a lot of potential. It can be reused for any A to B task, right? It doesn't have to be goal is here, source is here, once you have a map. But in any case, it has to be fast and it has to be robust against change. And the agent has to be robust against incomplete information, right? The map is not going to be fully, remember the code at the beginning. It's incomplete, outdated, could be outdated and so on. So let's get insights into and also the architectures and algorithms that, given that planning is worth it, what kind of algorithms, what kind of, for learning and planning and so on, right? Okay, so I'm more generally just compare different strategies. We're going to compare against very little memory or no memory. We call it greedy. So it has a sense, the agent has sense. And in an animal world, smell is very much invested in, right? So in the greedy, we assume it has a sense of which of the actions reduces its distance to the goal, which of the legal actions. We're going to have model-free RL and then planning-based ones. Yeah, so we're going to compare it and get insights into these different strategies in this simplified world. I mentioned it's okay to assume certain abilities are hardwired. For example, importance of states and that locations you can put it in your memory and associate it with what you saw at that location, or whether it was food or barrier in the neighboring radius one, and use that for planning. So we're going to assume certain things about the agents, and we'll have knobs, parameter on the difficulty of the problem and so on. For example, the size of the grid, or number of barriers, the proportion of barriers, or change, the motion noise. So we will have knobs to control these difficulties and see how these different strategies do. So again, daily task, go to food, and the first day you don't know where the food is, the agent doesn't know, and usually barriers change, but food might change too. Once food is reached, the problem resets to the next day. The agent gets teleported to the starting point. Barrier locations can change. So reported statistics on the number of steps to go on day 1, 5, 20, and so on, or median, max, mean, and so on. Average over several initial environments, the outer loop. So here you can see if you change the barrier proportion, you can have 0, knob 0 set it at 0, or 0.1. 10% of the cells have barriers, 20% and 30%, right? It gets harder. The path to food gets more intricate with higher barriers. And you can change, you have a knob, we have a knob for size. So 7 by 7, 15 by 15, up to 50 by 50. And then the barrier on a knob on change rate. So from day 1 to day 2, some of the barriers may change, right? So if it's 10% change rate, 10% of the barriers may change, and the overall proportion we keep it at, and we make sure there is a path to go. Okay. So the strategies very quickly. Our short paper has more details. So random is the simple you can think of, right? Pick uniformly at random from the legal actions that are available at any given point. Bias variant of random, a little bit memory, and does much better than random, is that don't backtrack. If you move forward, continue moving forward if at all possible. So it does require a bit of memory, or you might assume in physics world it's momentum or something. So greedy has this sense, and so there are 2 actions or 1 action direction that lowers its Manhattan distance to food. It takes that if that's available, if it's not a barrier there. And least visited is our exploratory. This is the first of our memory intensive strategies. So go to the adjacent cell with the lowest count, visit count, and every day it resets the path. It's kind of like model-free RL. Given the location, what action do I do? Learn a policy of that sort. So basically, it remembers the last action it did at each location, and that you can show it forms the path to goal. And the probabilistic map is most complex, that remembers from each location whether it was empty barrier food up to its experience, right? And does update that in a probabilistic way. I don't go into details of how it does it, but then uses that samples from that map to plan. And there are several possibilities that there might not be a goal. In the first day, you don't know where food is. And there were several cases that you can actually find. So we make a distinction between planning time failure and execution time failure, and so on. DQN is very successful RL model-free, fully observable, did really well on many, many Atari games. Yeah, but we couldn't quite make it work on this. And then we have a reference oracle. So here's the what different strategies use. Random is the simplest, doesn't require X, Y, the location of the agent, doesn't require smell, etc. It doesn't have any memory, no planning. Greedy requires a smell. Memory greedy is a variant of greedy that once you find where the food is, it remembers that. And so it needs multi-day memory to remember one piece of information, like where is the food, least visited, and so on. Path, DQ, and depends, but we give it the features of its surround and the location in particular. So the first two rows, it's every day is a brand new day. It doesn't remember much, right? These strategies don't remember. The subsequent rows, they do remember things from the past experience. Pure strategies won't work. So the way we have defined greedy, it technically fails if it gets to a corridor. But anyway, the barriers take all the greedy actions away. We can patch it simply, but it's better to do it in our more principled way of combining these things. So similarly, planning, it will fail in the first day. It doesn't know where goal, it has no notion of where goal is, right? We can have planning for exploration too. We haven't explored that in the paper. We haven't put that in, but that's possible too. But anyway, planning can fail. Some strategies, random is so simple, it never fails technically, but it's really bad. It's wasteful. In that sense, it's waste. It's very bad. But anyway, you need to pair these strategies with each other to get the pros and the benefits of multiple strategies. So for greedy, we pair it with bias in most experience because both are no memory or very, very, very little memory. Probabilistic map, we pair it with the count, the least visited count. So, but we need to talk about composite agents that use multiple strategies. And we have a very simple way of combining them. Round robin priority, the user, the experimenter sets it up. We can think about, learning this over time, and again, subject to change, right? As the board might change. But anyway, right now it's fixed. The experimenter, the user sets it up. It says, okay, strategy one, always start in strategy one, the beginning of the day. And if it fails or time's up for that, again, the time is given by the user. Go to strategy two and wrap around. If both fail, then wrap around. Yeah, the budget could be, the time budget could be a special, and we have a progressive way of, we double the time each time you revisit a strategy within a day. And that's a great way of, even if you don't know. 2 minutes, okay. And, okay, thanks. And yeah, so this is a way of architecture of combining these strategies. The agent tells them, okay, this is the action that was done by some strategy, the active strategy, then rest follow. And prepare at the beginning of the day, maybe you need to reset memory. So these are invoked for all the strategies. Some of them are simple, then they don't need to do anything. So the basic message is, yes, greedy plus bias does well. You see, this is 15 by 15 grid. Average over 20 days. Max is the maximum, really bad days. 30,000 on a 15 by 15 grid, where, if you had the full information, Oracle, this is just a reference, it would just take on average 15, median 14, and maximum 50. So it's a simple, and yeah, so anyway, greedy plus bias, bias is much better, greedy plus bias is much better than random. But probabilistic math plus least visited do the best. You can see 59 and so on. These are the realistic. This is the best of the realistic. And again, 0.3 barrier proportion, change rate of 0.1, so 10% of it. So probabilistic, so it's worth it. These show that if you had no motion noise, you get 7 times better as the barrier is increased. 7x better than using memory versus greedy, perfect sensing. So if sensing can fail too, the smell direction, right? The wind direction. It may not be available if you're too far from the goal. So 50 by 50, you can see it's much better if there's little motion noise. Even with change rate, you can get 30 times better or 20 times better. So, okay, you need extra machinery to keep track of where you are in the planning. You have to have a lot of memory, but it extends your agent's reach. So, but motion noise is the killer. So if you have the knob on motion noise, great, take it to 0.1, for example, every 10% of it moves, then the map is off some days especially. And you can show that, especially with grid size increasing, they can interact with each other, really kill any learning, any memorization. This shows that, hey, you need to update continually. You don't, after first day, second day, and so on, the steps are going down. It's learning, but it's not converged. The environment is changing. So you need to keep learning, keep updating. If you don't, if you stop learning, your mean or median number of steps shoot up. Okay, so that's that. So but the basic finding is that memory can help. It does require infrastructure and so on, but it can be substantially better than simpler no memory, little memory strategies, as long as motion noise is the thing, even though your map is imperfect. So world is large and dynamic, and just have limited access to it. World is a structure too, so that motivates learning. But there is change on the side. Some things will change. And so we need that challenges learners. We looked at several range of strategies, and we showed that on the right algorithms and architectures, yeah, it does pay dividend as long as uncertainty, and especially in motion, is limited. So future, more learning, more regularities, basic RL. How does the agent know that if the action, what the effects of actions are? How does it granularize space and time, enrich perception, and so on? Yes, so that's that. Code and longer paper under preparation. Thank you so much, and that's it.
Okay, thank you so much, Mr. Omid. Someone else? Okay. Any questions? Yeah.
Hi, Omid.
Hi.
The question is, my name is Victor. If you plan the learning classifier systems in your research?
We use DQ. We haven't used classifier system. The most from neural networks, we use DQN. It up to certain change, like a point, it couldn't handle 0.1, but certain changes, such a barrier portion, it could handle if you waited for many, many days, like hundreds of days. And again, some days it had really bad days. We played with the temperature, with the learning rate. We haven't been able to make it robust. So it wasn't in the table that I showed. So, but if I understood correctly, yeah, we haven't played with, if I understood correctly, with other techniques like classifier-based techniques and so on. But if you have pointers, definitely welcome to share with me. Thank you.
Hello, very interesting. I enjoyed it. I've got two questions. So you mentioned DQN, so these model-free reinforcement learning algorithms. What model-based did you try? Model-based? That's sort of like a classic model-based out there.
Good question. There are classic model-based ones that what they learn is maybe the dynamics of the world. We haven't played with those, but yeah. So I know about, like, model-based usually means MDP, learn the MDP or POMDP. Yes. Again, we are trying to go to transformer-based because those are hot now. But yeah, if there is anything else that we should compare, because again, they usually assume the world is static. The goal is not changing. It might take a while to the reward, but if the world is changing every few days, if the barriers change, if the food changes, I don't think
Right.
they are. Yeah.
Yeah,
But
I was definitely
it would be good to
curious.
have
Yeah.
baselines, good baselines, definitely.
Yeah, I
Go ahead.
suspect you're right that if you have a really non-stationary problem, that those techniques probably do kind of assume things are more or less stationary. In my work, we were kind of looking at the Dreamer V3 and some of those other ones that are kind of newer, and so far we haven't been able to get those to work very well, but I was curious if you had any luck with that. So the other question I have is related to, so if you have a environment that's say 95% static, but there's a small section of the map that might change regularly, have you looked at sort of isolating sources of change or areas of change with some kind of attentional mechanism or something that says this area needs work, but everything else can be kind of assumed that your model works?
Yes. So that's the question. I think the world is fairly static, but you never know what will change. But it's again a technique you mentioned, like attention or something. We want to compose, we want to concatenate different worlds, and we can do that to some extent. And yeah, so at one point the barriers were 30% of the world, and then at another point becomes basically barren, no barriers or 1% or something. But some other challenge comes up, like drought or something. Yeah, so we would like to do those things. And regularities, as you mentioned, there might be some regularity that some corner of the world is changing, the rest is not changing. Can you learn this? But again, under a specific thing that nothing is guaranteed. Someday the things that you thought are not going to change, and those things that so whatever the regularities you learn, hopefully they are all subject to some flexibility of up modification. Whatever map you learn, other skills you learn, that's our hope, that we're not gonna tell the agent, oh, maybe for many years something won't change, but suddenly it changes. Yeah.
Yep, exactly. This seems like where consciousness comes in, right? You try to automatize anything that seems like it's super static, and then you have
Ooh,
to sort
meta
of,
learning, for example, consciousness, meta learning. Yes, there are things that have been done in our L world, like meta learning. Yes.
Thanks so much. I appreciate it.
Thank you.
Okay, thank you, Dr. Madani, for your talk. So let's continue with the next speaker, Irvin Uriel. Are you ready? Irvin, are you here
Sí,
with us? Okay.
sí, aquí estamos.
Okay, Irene, you have 15 minutes and 5 for questions. Go ahead.
Ok, gracias. Bien, pues voy a comenzar con mi participación presentando mi proyecto de investigación, el cual tiene como título Adaptive Neurofuse Inference System for Modeling the Influence of Process Parameters on Pulsed Electrochemical Machining of AC-1018 Steel. Bien. De manera general les voy a platicar una breve introducción, el planteamiento del problema abordado en esta investigación, el estado del arte, la hipótesis, la metodología, los resultados y finalmente unas conclusiones. Bien, de manera general, el campo de aplicación en el cual se encuentra ubicado este proyecto es en la industria metalmecánica. Este tipo de industria se caracteriza por la transformación de materia prima, en este caso piezas metálicas, a componentes con características y dimensiones específicas que ya son utilizadas en otro tipo de aplicaciones más avanzadas. Este tipo de transformación se realiza normalmente mediante algunos métodos de manufactura, como son técnicas convencionales y técnicas no convencionales o técnicas de manufactura moderna. Eh, en este orden de ideas, en este proyecto se encuentra el maquinado electroquímico por pulsos, o PEC, el cual está constituido por una serie de elementos como son un electrodo, un electrolito con propiedades conductoras, una pieza de trabajo, una fuente de polarización, que al estar energizado permiten desgastar material de la pieza de trabajo sin necesidad de entrar en contacto directo con la herramienta. Esto se logra a partir de la transferencia de electrones desde la herramienta hacia la pieza, eliminando material de manera molecular, lo que permite eliminar el metal sin requerir tanta energía. Bien, antes de, bueno, a simple vista pareciera que este proceso es relativamente sencillo. Sin embargo, la complejidad se sitúa en cuánto o cómo controlar, cómo entender cuánto material estoy eliminando para alcanzar las características que yo deseo. Para poder abordar este tema, primero se realizó el análisis en sí del proceso de maquinado electroquímico por pulsos, el cual puede estar constituido por una serie de parámetros del proceso, que son las variables que permiten regular cuánto material se está desgastando. Según la literatura, se puede encontrar que existe el voltaje, la corriente, el área de exposición, la frecuencia y la distancia entre electrodos son las variables que tienen mayor relevancia en este proceso de manufactura. Sin embargo, se puede cuantificar el rendimiento de este proceso mediante una serie de variables como son la tasa de remoción de material, el sobrecorte. En este caso, la tasa de remoción de material describe cuánto material estoy eliminando con relación a la configuración de los parámetros del proceso. Y bueno, otra variable muy importante es el sobrecorte, el cual me va a permitir describir el error que existe entre las dimensiones que yo estoy obteniendo en mi proceso de manufactura con las dimensiones que yo esperaría tener. Bien, en este caso, como planteamiento del problema, se estableció lo siguiente, en cómo modelar precisamente el comportamiento de la tasa de remoción de material y el sobrecorte del proceso de maquinado electroquímico por pulsos utilizando estrategias computacionales. Bien, en el estado del arte se pueden encontrar una serie de investigaciones en las cuales se han abordado el modelado de técnicas de manufactura moderna, como es el maquinado por descarga eléctrica, el maquinado electroquímico, y se han utilizado una serie de estrategias, como puede ser la lógica difusa, las redes neuronales artificiales, modelos híbridos que integran más de una técnica. Se puede observar, según el análisis de estas técnicas, que, bueno, se tiene gran dificultad para modelar esos procesos debido a que son procesos industriales bastante cerrados, es decir, no se tiene información abierta en sí de los datos que se utilizan en cada estrategia. Entonces, bueno, al utilizar estrategias computacionales se tiene este problema, ya que una estrategia computacional necesita de muchos datos para, pues bueno, mejorar su rendimiento, como es el caso de las redes neuronales artificiales. Se han optado por utilizar otro tipo de métodos como la lógica difusa, que son más robustos ante la imprecisión, ante la ambigüedad de los datos, que bueno, esta es una técnica bastante útil en este tipo de procesos de manufactura. La desventaja que tienen es que, bueno, son técnicas basadas en la experiencia, entonces se necesita de una experiencia sólida para poder plasmarlo en este tipo de técnicas computacionales. Por esta razón, se han implementado otro tipo de estrategias como es ANFIS, las cuales integran los beneficios de las redes neuronales artificiales para realizar algoritmos de predicción y se integran con la lógica difusa para ser más robustos ante la ambigüedad, ante la carencia de los datos. Pero aún así existen dificultades, ya que los procesos de manufactura suelen ser bastante complejos. En este caso, bueno, se han abordado diferentes puntos de vista y se ha llegado a la conclusión de que algunas estrategias de optimización pueden ser bastante útiles para mejorar aún más el rendimiento que tienen estas técnicas para realizar predicciones en problemas que tienen gran complejidad. Bien. Por lo tanto, como hipótesis de esta investigación se planteó lo siguiente: en si la implementación de un sistema adaptativo de inferencia neurodifuso optimizado permitirá describir con exactitud la relación entre la corriente de maquinado, el voltaje de polarización, el gap, el área de exposición, que son las variables o parámetros del proceso, con respecto a la tasa de remoción de material y el sobrecorte en el proceso de maquinado electroquímico por pulsos. Bien, como objetivo general, pues se pretendía redesarrollar un modelo ANFIS, en este caso optimizado, con el algoritmo genético y haciendo más específicos para predecir las variables de relevancia que permiten describir el rendimiento, como son la tasa de remoción de material y el sobrecorte. Bien, les voy a presentar de manera general la metodología empleada. En primer lugar, se realizó la integración de un conjunto de datos, ya que como lo mencioné, pues estos procesos de manufactura no tienen como tal datos abiertos, entonces se tuvo que generar un conjunto de datos utilizando los principios reportados en este tipo de técnicas de manufactura. Se utilizó un diseño experimental factorial 3 a la K. Posteriormente se llevaron a cabo las pruebas experimentales utilizando un prototipo de manufactura PEC. Se cuantificaron los resultados y finalmente se organizaron para su posterior uso ya en el algoritmo computacional. Bien, como tal, como resultado de este proceso experimental se generaron 270 experimentos, lo que permitió obtener en este caso los patrones que se implementaron en el algoritmo, en ANFIS, donde los atributos resultantes fueron el voltaje, el gap, el área de exposición, la corriente y la frecuencia, y como variables de salida, la tasa de remoción de material y el sobrecorte. Bien, con estos datos se aplicó posteriormente un análisis de correlaciones Spearman para identificar si efectivamente las variables que se estaban proponiendo para este modelo eran significativas. En este caso se logró identificar que la frecuencia tenía una correlación bastante cercana a cero, lo que indica que es una correlación bastante débil. Esto significa que la frecuencia tiene poca importancia para con las variables de salida. Por esta razón únicamente se quedaron como variables de entrada la corriente, el voltaje, el gap y el área de exposición. Con estas variables, bueno, son las que se utilizaron como parámetros de entrada ya directamente a la arquitectura del modelo ANFIS, el cual está constituido por una serie de etapas o capas, donde la primera es la capa de premisas, ajá, donde se encuentran unos parámetros denominados parámetros de premisas. Estos parámetros están constituidos por funciones difusas que permiten ponderar las variables de entrada a grados de pertenencia. Con estos grados de pertenencia se calculan la fuerza de disparo que tiene cada variable con relación a lo que se desea modelar, se normaliza, se calculan los parámetros consecuentes y finalmente se obtiene una predicción. Ajá. Donde cabe destacar que los parámetros de premisas, es decir, las funciones de membresía, sirven o tienen una gran relevancia para permitir ponderar las variables de entrada y así generar una predicción cercana a los datos esperados. Bien, lo siguiente fue dividir el entrenamiento en dos etapas. La primera etapa consistió en entrenar el modelo ANFIS utilizando los métodos convencionales, es decir, un modelo ANFIS convencional. Este tipo de modelo trabaja mediante el descenso del gradiente. Ajá. Y bueno, se ha identificado en la literatura que este tipo de entrenamiento tiene ciertos problemas cuando el fenómeno a modelar es bastante complejo. En este caso, por eso se propuso adicionar la optimización del modelo ANFIS utilizando un algoritmo genético. Y bueno, esto va a servir de referencia ya que va a permitir observar si efectivamente se tuvo una mejora al optimizarlo. Bien, les voy a presentar parte de las características de la optimización. En primer lugar, lo que se va a optimizar son los parámetros de las premisas del modelo ANFIS. Estas premisas están constituidas por funciones. En este caso, se utilizaron funciones de tipo gaussianas. Estas funciones se pueden generar mediante el centro de la función y el ancho de la campana o de la función. Y bueno, entonces se necesita optimizar el centro y el ancho, donde el ancho se optimiza mediante un valor de desviación estándar. Entonces, para cada función se necesitan dos parámetros. En este caso se tienen cuatro variables de entrada y por cada variable de entrada se tienen tres funciones de membresía. Si por cada función de membresía se ocupan dos parámetros, se tiene un total de 24 genes, los cuales conforman el cromosoma. Se está utilizando o se utilizó como función objetivo el promedio del coeficiente de determinación tanto de la tasa de remoción de material como del sobrecorte. En este caso se le da una importancia igual a ambas variables.
2 minutes, Irving.
¿Ok? Bien, entonces aquí les voy a presentar los resultados. Esta es una gráfica de convergencia en la cual se puede identificar que efectivamente al adicionar el algoritmo genético se logró optimizar el rendimiento del modelo para predecir las variables de estudio. Aquí en esta otra gráfica les presento el coeficiente en la etapa de prueba, en donde se puede observar que el modelo optimizado efectivamente logró mejorar el rendimiento de las predicciones, obteniendo 0.94, 0.92 para el sobrecorte y la tasa de remoción de material, mientras con el modelo ANFIS, mediante métodos convencionales, alcanzaba un coeficiente máximo de 0.88 y uno de 0.84. Adicionalmente, se evaluó también el error cuadrático medio, donde se puede observar que efectivamente al optimizar el modelo ANFIS mediante el algoritmo genético se logró disminuir este error. Aquí también les presento estos gráficos de dispersión en donde se puede observar la relación que existe entre las predicciones realizadas por el modelo con relación a los datos esperados. En este caso, esta gráfica es para el sobrecorte. En esta otra gráfica presento el gráfico de dispersión de las predicciones y las observaciones, ahora de la tasa de remoción de material. Se puede observar que se realizan predicciones bastante buenas sin realizar predicciones con un sobreajuste. Ya casi para terminar, aquí les presento estos gráficos de errores en los cuales permiten o permitieron aplicar la prueba Bretush-Pagan, la cual indica que las predicciones tienen homocedasticidad, lo que indica que las predicciones tienen un comportamiento confiable, tienen estabilidad, ya que no tienen una varianza constante y no tienen a sesgarse conforme se realizan las predicciones. Estas son las funciones que se obtuvieron en la optimización. La primera es para la corriente, la segunda para el voltaje. Esta otra son para el gap y para el área de exposición, las cuales permitieron en este caso obtener el rendimiento antes mencionado. Bueno, ya para terminar, aquí presento estas conclusiones, en la cual la primera es que, bueno, el modelo ANFIS, entrenado mediante métodos convencionales, encontraron una solución local debido a la complejidad del proceso a modelar, lo cual se observó en el gráfico de convergencia. Como segunda conclusión es que la integración del algoritmo genético al modelo ANFIS permitió incrementar la exactitud de las predicciones, en este caso ya al obtener un óptimo global. Y finalmente, que la implementación del modelo ANFIS optimizado representa una contribución, digamos, significativa al modelado inteligente del proceso de manufactura PEC, ya que este enfoque no solo mejora la capacidad predictiva del sistema, sino que también aporta una herramienta robusta para comprender, controlar con mayor precisión el efecto de las variables del proceso, lo que puede ser aprovechado tanto para optimizar la calidad en entornos industriales. Bueno, esto prácticamente sería todo. Muchas gracias por escucharme. Quedo atento a si tienen alguna pregunta.
Hey, thank you so much, Irving. Just to remember, all the presentations must be in English for our auditory. And well, does anybody has a question for this work? No. Okay. So thank you so much, Irving.
Thank you.
Okay, let's continue with the next presentation performed by the speaker, Isaac Rocha.
Hi. Well, I have 15 minutes and 5 for questions. Okay, I'm Isaac. It's a pleasure to have you here in Mexico. Today I present you the work called How Consciousness Modifies the Motivation of Belonging in Agents. So, go ahead. Okay, sorry. Sorry, okay. Yeah, okay. Well, the content of this presentation is as follows. To contextualize the work, an agent is a computational system situated with an environment capable of performing autonomous actions to achieve its objectives. However, the situation becomes more complex in case of multi-agent systems, as multiple entities are involved. And precisely because of many problems require collaboration, leading to more complex behaviors. As a result, group membership becomes essential for achieving goals that are difficult or impossible to reach alone. In humans, the motivation of belonging is a powerful force. It drives us to collaborate, to adapt to social norms, and to seek acceptance. Let us imagine an artificial agent participating in a collaborative work group, such as a team of exploratory robots interacting with humans. As it engages with the group, the agent receives signals, praise, corrections, or temporary exclusions. Could the agent develop a sense of belonging? And what if it were also capable of being aware of that feeling and adjusting this behavior accordingly? If the agent is aware of these signals, it can develop and update its sense of belonging, which already impacts its motivation to remain in the group and contribute to the achievement and shared objectives. But how can we understand these behaviors? Theory of mind refers and offers an approach that enables the understanding of such behaviors, beliefs, desires, and intentions, and provides a framework for interpreting their diversity. A classic demonstration of this is false beliefs help us to understand how others can hold their incorrect or different beliefs from reality and from our own. And for example, believing on oneself to be part of a group that is not a case. But certainly, we need a way to model and construct such behaviors and provide them to the agents. This work adopts a bio-inspired approach which, through cognitive science and architectures, aims to map these capabilities and implement them in computational systems. Quajojotl is an architecture proposed by the Nicolak Group, offering a framework to build these models that enables endowing agents with intelligence to the understanding of cognitive science. To address these issues from a cognitive science perspective, we consider the experiments conducted by Haggard. The brain, when given a goal, anticipates the execution of a task, and showing neural activation will before to the action is performed and long before the desire. This process remains unconsciousness, and then we can take action for the I'm conscious. But what is consciousness? No, it's a big question. Haggard found that we're conscious of something when we can verbalize it or report it. And this precisely is why consciousness is important. It enables focus on a specific content and facilitates proven decision-making regarding it. Through this process entails a significant cognitive cost, but I regard myself being conscious of something. Well, a very interesting part is volition. Volition it involves deciding whether to act, which action to take, and when to perform it. Okay, for this work, consciousness is the ability to recognize the information one has, evaluate the information, and act on that evaluation in relation to the present circumstances. Okay, the scarcity of models incorporating dynamic and adaptive mechanisms for consciousness activation poses a significant limitation for artificial agents, particularly because the lack of elements that replicate socially aware and self-perception within the group environments, thereby hindering the ability to adjust behavior according to their social role or status. And this is important because understanding the mechanisms by which an agent becomes aware of its own social status is fundamental to modeling social intelligent multi-agent behavior. Some application areas, we had social robotics and assistance, robots that adapt emphatically to users' emotions and social cues, and security and intelligent monitoring systems that detect abnormal behavior and assess confidence before responding. And obviously, video games and simulations, NPCs with social behaviors that learn and adapt within a group dynamics. Okay, a little revision of the state of art. Based on the above, we decided to evaluate 5 key aspects we consider essential for building a social grounded group consciousness, supported by the background review. We had a threshold of consciousness. This component determines when a social interaction warrants high-level attentions, theory of mind and false beliefs, social consciousness of the group, belonging motivation, and belonging as an evaluated state. These elements were reviewed under large architectures, obtained these results, and well, so addressing these gaps is essential for advancing toward more human-like artificial agents capable of rich and more adaptive social behavior in complex environments. The proposal of the work is a computational model where an artificial agent develops a sense of group. Okay, a sense of group like inclusion or exclusion. And belonging emerges and evolves through the consciousness threshold triggered by social silent feedback. By integrating predictive processing and theory of mind, the agent detects discrepancies between expectations and social signals, enable belief adjustments that reinforce or challenge its group membership status. Okay, returning to the Hagar experiments, there is an accumulations process when it's building a reach certain threshold and catalyzes consciousness too when we become aware of what we intend to do. A decision is made followed by action. But it's more complicated because in the literature review did not provide specific quantitative values for reaching these thresholds. But we can identify 2 thresholds. The first, become aware, and then we can take action. For the proposal of these thresholds are modulated to continuous feedback from the environment, enabling the revision of internal beliefs and the simulation of consciousness processing with respect to the specific information. The functions we propose is an accumulated social feedback, and the agent needs to interpret the actions and intentions from others for its partnership. And okay, The interpretation of these stations varies from an agent to another, and one may perceive as a negative, another, and may interpret as a positive. And another is the source of the feedback relevant and influence the weight that the feedback carries. Okay, sorry. Yeah. This allows us to integrate a new state into the belief system, the state of doubt. This state equips the agent with the ability to resist its beliefs and emerge from the contradiction between the belief itself and the feedback received. We model the above as a photo. Okay, we can say the agent becomes aware of his belonging when he crosses the first threshold, the threshold of doubt. This is a diagram summarize the process by which an agent interprets social signals, and it functions as follows. The agent begins with a belief or inclusion or exclusion, assigning it it's a true or false value upon receiving a feedback. The agent interprets it and proceeds to either revise or confirmation of the initial belief. This is a general idea. If I had a belief with value with true value of positive and the feedback is negative, then the agent needs to change its initial belief. Another key point to consider is the feedback is dynamic, and the deltas contributes the accumulation of processes is varying ways. This gives a rise to borderline cases. Depending on the value of delta, we have unconsciousness, when delta is below the Dove threshold, conscious when delta surpasses the Dove threshold, and active when delta exceeds the action threshold. For the case study, we put in 5 agents forming a social bond and developing a sense of belonging at the university. They adapt their beliefs and social identity through feedback and false belief detection. And modeling cognitive flexibility and using theory of mind. Well, the hypothesis of this work is when an artificial agent receives enough social feedback that contradicts or reaffirms its initial beliefs of belonging, then it will be able to revise this belief and become aware of it and adjust its social self-perception, increasing the accuracy of its position in the group. The objectives of this case study is demonstrate that consciousness awareness of inclusion or exclusions from a group contributes to the motivation to belong, and to analyze social feedback helps validate or reject beliefs. Okay, feedback works, provides feedback. A group of agents provide feedback to one of its members, and this agent internally forms an interpretation of the feedback, although he does not become aware of until he has accumulated enough information to realize it. When he becomes aware of the information he possesses, he can then decide based on it. Okay. This graph presents the results of the conducted experiments. The agents become consciousness and then makes a decision. For this case, the feedback, it was positive, so the agent confirms the belief. And these results obtained, the agent interpreted mostly as a negative feedback, so he had to challenge his belief. Some conclusions: foundation for social intelligence, and consciousness precedes decision making. Belonging is a reflective process, and both trigger consciousness. for the agent's current goal. The identified functions are still being developed and focusing on the internal mechanisms behind conscious decision making. And thresholds are dynamic and context depends, shaped by each agent's unique experience. And that is all. Thank you so much.
Any question? Okay.
Hi. It's not so clear to me what exactly are your claims, because consciousness is a quite complicated phenomena. So some people, for example, Block differentiates between phenomenal consciousness, access consciousness, monitoring consciousness, self-consciousness. Some issues like inner speech appears to be related to consciousness, but it doesn't seem to be the case that the kind of consciousness that you are addressing is able to fulfill all these spectra of different possibles of consciousness. It will be interesting to understand better which kind of consciousness that you are modeling with your model, because at least to me, I think that you are making an advancement in one direction, but it's not so clear what is the direction and what is the kind of consciousness that you are actually modeling with your proposal. So if you can clarify that.
Yeah, thank you, Doctor, for your question. Well, for this word consciousness, I get started and when I can say I'm conscious for something, and this is the focus of this word. Give agent to the capacity of consciousness. I don't know. The agent can say, I'm conscious of my belief when I can go back for me. This is, well, is the a phase, initial phase of consciousness, but the intention is this: when I can say I'm consciousness of something.
But this is tricky, because if you think about you, it's one thing, but imagine, for example, that you have a robot, and this robot has a planning system, and this planning system creates a plan, and after some time it decides to apply this plan. Do you believe that this robot will be conscious by your definition? Because at some point it first generates the plan, and then after some time it applies this, it decides to apply.
Yeah.
It will be a conscious robot in this case.
Yeah, if the robot can verify the information he had, then the robot can be consciousness. Okay, he received feedback from the environment, and if the feedback contradicts this initial objective, the robot needs to verify. Well, we need to pay a high cost of this, but the robot, I think, can be consciousness.
Okay, okay, thank you. We can discuss later. Thank you.
Any other question? Wait a minute.
I think it's very important to work further on the definition of consciousness, and so I believe this is a work in progress, right? Research, and I think so far what you have covered is maybe some sort of interactional consciousness. So the agent, so the level of consciousness that you are and the kind of consciousness that you're defining, it's related to the interaction of the agent with the environment. So the highest the interaction, the more the consciousness of the agent is. But still, you have to go deep into the concept and maybe define some sort of computational consciousness, and maybe move a little bit away from psychology, from sociology, from this, because that's very ambiguous. But if you make it more computational, I think the problem can be better approached. Thank you.
Thank you, Doctor. Actually, as Dr. Kugel exposed before, we have a consciousness part of algorithmic and experience of consciousness. So some authors calls qualia, and it's a complex part of consciousness. How can I feel the red color? How can I feel the sunset? It's more complicated, but for this part, the algorithmic part, this work is in progress. No, we explore all these terms.
So I had similar questions about sort of your concept of consciousness overall. It seems to me, just thinking of how what you describe functions in the system, you have a gate for the action ability, right? So you have something, you're waiting for a certain amount of certainty, and once you have certainty, you are allowing action to occur in your system. So does that sound like availability of your, say, sense of belonging is the thing that's sort of being thresholded? And once you get to a certain point, then you're allowing your agent to take actions based upon it. So availability of this to an action selection or action execution kind of process.
Okay. The way of the model this is from data structure. The agent can interpret the intentions of another agent. We provide them weight and values of true. Then when the agents interacting, they with a function extract the value of this intention, and then we can accumulate this feedback. Again, it's a proposal and this initial work, but I don't know, Doctor.
Yeah, no, I'm not trying to pick on you or anything like that. Just you have a threshold, and the threshold was based on the line that you had in your graph. How do you cross over the line? What's the quantity that would be crossing the threshold?
Okay, you refer to y in the middle, and then
yes, on your y-axis you had a horizontal dashed line. I think it might have been yellow. I'm not sure,
okay.
But that was something that was controlling conscious awareness.
This is actually the current work. The thresholds are dynamic and it constructed by our experience, etc. But we take the idea of Hagar, in which brain prepares given a goal and reach a certain threshold, then take action. So this is a form I model with this idea.
Okay. Yeah, we can discuss it more afterwards.
Yeah.
I think it'll become clear. Just informal talk. But
okay.
Thank you. I appreciate it.
Thank you.
And thank you for diving into consciousness.
Thank you, Doctor.
It's over. It's over. Question. Now
we can talk later, Doctor.
Please, Doctor.
Excuse me, we need to follow the schedule. Thank you so much, Isaac. So,
Okay,
want to talk before.
It's my pleasure to introduce Alexis Sansnovich. He's a professor in cybernetic department of the head of BICA lab in the Institute of Cybernetic Intelligence System at the National Research Nuclear University in Moscow, Russia, an affiliation faculty in the Department of Bioengineering of George Mason University. He holds a PhD in applied mathematics from University of Arizona, where he co-developed a continuous attractor theory of the hippocampal spatial maps and mental state framework for cognitive modeling. Since 2000, Professor Sansnovich worked in the Croswell Institute of Advanced Study of George Mason University, where his highest rank was assistant professor. Since 2005, his research focused on biologically inspired cognitive architecture, and since 2012 on social emotion BICA. Professor Sansnovich is the founding chair of BICA Conference Series, founding president of BICA Society, founding editor-in-chief of the Journal of BICA and BICA AI section of Cognitive System Research. Professor Sansnovich, you will have 40 minutes to present your topic.
Thank you, Rogelio. Thank you very much for your beautiful introduction. Those are mostly achievements of my past, but now I think I deserve to do what I want, and this is what I'm doing. I would like to tell you some perspective on possibility of further development of AI based on BICA and LLM and their integration. And I would like to start with this analogy of John Laird, which you see in the background picture. So actually this background is the slide of John Laird that he used to explain what are the capabilities of AI today. That was taking place before the latest developments with LLM. The white bright dots represent things that we can do with AI, and the black background is what we cannot do. So the AI was very specialized on particular tasks. For comparison, if you look at human abilities, it covers virtually anything. So a human can take any task and do something rational about it, not necessarily achieving results, but in most cases, doing something that is not absurd or ridiculous. And if we look now at large language models, they also seem to be somewhere in between, like they cover a large area, they are fluent in language and can speak about anything with anybody in any social environment, but still cannot do too much. There are many things that still only humans can do. So we want to have an AI in the future that covers all the human abilities and does it even better, plus maybe some tasks are performed at a very high level. So this is the general wish. Now, how do we achieve this situation? So this is the plan, approximate plan of my talk. First, I would like to discuss questions about LLM and BICA, like what LLMs are missing, what BICAs can do, and how to integrate them. And then I will describe a particular way of their integration, including social emotional BICA, formal model of semantic space, moral schemas, and hybrid agents based on BICA and LLM. So let's see how it goes. And first, I would like to remind you what is BICA. Of course, cognitive architecture is not just an architecture, it is a blueprint for designing intelligent agents. It is a complete system that includes the entire cognitive loop from perception to cognition, decision-making, and action. And it has a memory system which is similar to the human memory system, like it includes working memory, semantic, episodic, procedural, sensory memory, and so on. I would say that all cognitive architectures, in my view, are biologically inspired because the original goal of this direction was to understand how the human mind works and replicate it in the computer. And this is what they do. They actually are in between those realistic brain models that are difficult to create and mostly they have no practical use, and very abstract psychological models that have only descriptive powers but cannot compute anything. So BICA can compute real thing, can do tasks for particular paradigms, and they also are sufficiently abstract to be relatively easy to implement. Still, this is not as easy as we would want it to be. So you see the BICA bridges the gap between precise neurophysiological models and higher abstract cognitive and psychological models. And so therefore, this is the approach that will give us was supposed to give us breakthrough, but it did not happen. So why? And instead, we have now a revolution of large language models, which some people believe can do everything, and we do not need anything else. No, this is not the case. And you see in the left column, I listed some things that LLMs are missing, like they do not have a sense of self or subjectivity. They do not have agency. There is no reason for it because there is no architecture of an agent like in BICA. Therefore, they have no motives, no free will, goals, or desires on their own. They would not do something like their own goal settings, dreams, and plans for the future. They do not have emotions or personal experiences. They do not have personality or personal relations. Well, there were some attempts to give them those qualities, and you could say that maybe I am not aware of something, but the fact that the modern ChatGPT or DeepSeek are deprived of those features intentionally tells us that probably those attempts were not successful because it's not an agent that can have a soul in the sense of a human. So also this approach excludes the usage of scientific domain knowledge. Instead, any knowledge is treated as big data and you use statistical models to describe those data. And therefore, I could call it a statistical AI, this approach, as opposed to cognitive or symbolic AI, which is basically represented by BICA, not only BICA, of course. And so BICA is nevertheless unique in the sense that it can have those features that are listed in the left column. Not necessarily they do it now, but we know how to implement those features. What they cannot do, well, in principle, it would be possible theoretically, but practically it's difficult, like give them fluency in natural language, common sense applicable to any real world situation, ability to make cross-modal inferences without prior symbol grounding, or the ability to autonomously grow cognitively, learn on their own. Well, they learn, but they do not grow. So they mostly stay at the level at which they were designed by their designers. And this is also another major difference between the two kinds of AI, because statistical models, like the human brain also, they develop on their own. BICA, if they are engineered and have definite structure, they cannot change their structure no matter how they learn. Well, there were also such ideas, but at least they didn't lead us to a breakthrough. So the brain is an interesting example because it is a BICA on the one hand, and also a statistical model, I would argue, on the other hand, because it learns by itself. So it tells us that there is a possibility to have both in one system. And therefore, the question is, how do we really integrate those two things? And this is the question that I believe concerns all researchers who are working in this field today. And there are many ideas for such integration. So I would like to discuss one possible idea. In this case, I would consider verbal communication, like a dialogue, in which, well, the purpose could be anything, like any service, any agent interacting with a human. To be efficient, it needs to understand human mentality, not just understand what the human says, but also what the human feels and what is on his mind. And therefore, we need to understand not only what is being said, but also how it was said, in what tonality, in what flavor. And there are numerous approaches to this kind of understanding, starting from sentiment analysis, which turned out not sufficient. So today we have tonality analysis, which has multiple scales like detecting formal, informal tone, detecting insult, sarcasm. And the list is not actually very long. So there are maybe a dozen of such things that can be effectively detected today with tonality analysis, but there is no system and there is no completeness in this domain. We also have various models of emotions, like basic and complex emotions. There are so many models that it's difficult even to mention them, but this is limited to emotions only. And if you take something like expressing moral support, asking for assistance, or criticizing, or that would go beyond emotions, and we need to understand those things too. So how do we generalize and build a complete model of all possible human intentionalities? There are actually too many of them. If we start listing, we would have billions of those intentionalities, and it's not clear how to deal with them. So the approach that I would like to describe is based on two notions. One is intention, another is intention. So there are two words, two terms in science, and they used in many fields. And I would like to describe a possibility of building a general formal model of those things, like intentions. And what's the difference between them? Intention tells us the direct objective of an action, like what the person wants, like order a dinner or buy a ticket or open an account. But if you are talking about intention, that means a connotation. In this context, it means how the person tells about it, with what feeling, with what predisposition for a certain kind of behavior, which reflects the attitude of the speaker, the relation to the interlocutor, and therefore it has a second layer of semantics, so to speak, which is important. It is not actually taken into account right now in most applications, but without it, humans would not be able to understand each other. So we need to give this ability of understanding to the artificial agent, and therefore we need to build a framework, like a formalism for detecting and operating with those things. So here are examples of intentions which characterize just like a person feels about somebody and what's the attitude or predisposition toward the interlocutor. Here are some requirements that allow us to distinguish intentions from other possible flavors of speech. And we have a table in which you see already a separation between two antonym pairs. Now I would like to talk about relations. Okay, so here are more examples of antonym pairs of intentions. I hope you got the notion of intention that I just described and how it differs from intention. Now we dive into various kinds of relations among those things. And we consider antonymic complementarity, anti-complementarity. Actually, that's something that I invent on the fly because it means just the antonym of what is complementary. Also, the pairs of active-reactive counterparts. And there are many more relations, but these are actually useful for building some kind of a graph or system of intentions. And you see examples in the table here. And here is more explanation, like for each given intention, here I1, we have its antonym, we have its complement, which would be a response that is natural in the given situation. The opposite response, which is not natural, would be anti-complementary. And those both are reactive. Each of them has an active counterpart. Those active counterparts in turn have complements, anti-complements, and so on. So this is the general template according to which you can build a graph of intentions. Now, I would like to show you a few examples of fragments of such graphs. Like if you start with expressing moral support, the opposite to it would be criticizing. The complementary would be gratitude, respect. Anti-complementary would be assertive, anti-patronizing, and so on. If we start here with call for frankness, then the interlocutor could be open, frank, or could be on the opposite, closed and evasive. And in this case, the graph actually closes quickly on itself. In another example, like formal tone, informal or assertive, informal tone or assertive tone would be also closed on itself, and other graphs are closed after many steps. So here are more examples. Like two people meet on the street and greet each other. They can greet each other, or one of them can ignore, or the first one can ignore. And so these are all possibilities that are closed in a structure shown here. Similarly, being honest or dishonest, trusting or distrusting also has a graphical representation. Provoking, ignoring, reacting. Such things also have similar representations. So these are precursors for what I will call later moral schemas. These are not moral schemas on their own. I will explain what do I mean by that term. For now, let's say there are certain kinds of relations between intentions, and based on those relations, we can establish a graph of links between intentions, and here's the result. So when we listed 125 intentions, we constructed a graph of them, and it turned out to have this structure with statistics described on this picture. We then trained a distilled bird to recognize those intentions in speech acts, which makes it suitable for perceiving information in terms of vectors of intentions, in addition to semantics that we extract from speech. And we showed that actually it's fairly accurate. Okay, so then after some linear algebra, which is actually a known procedure called whitening, I'm not going to describe details. we compress the space to 92 dimensions in which those intentions are not orthogonal. We actually now have angles between them telling us how much they are mutually dependent or similar. And this model actually shows us the semantic space for representation of intentions. Okay, what can we do with it? I say this is what we need for constructing so-called moral schemas. So now what do I mean by moral schema? Actually, I found that in the literature that combination of words moral schema was used even before it came to my mind, and usually people mean something very narrow, descriptive in the studies of ethics and morality. And this is not, by the way, what I mean by a moral schema. So here it is a term that is defined independently of other uses of this term. By a moral schema, I mean not just a schema, not just a template, but actually a device, an agent on its own, which has no identity, but it has a purpose, a motive. The motive of this agent is to achieve so-called normal state, the state of affairs that is considered normal. And this is its only purpose, and it can be achieved by all available means, by modifying the agent behavior. So when moral schema is activated in the human brain or in some artificial agent, and it starts influencing the behavior of that agent toward maintenance or achievement of the normal state. Now, the normal state is actually a state of mutual relations among agents that satisfies certain conditions. Those conditions are basically expressed by feelings. So feelings are appraisals of agents by each other. So basically, these are relations among the agents. Inferred from, appraisals are inferred from their behavior, but feelings are set a priori. Those are beliefs of what is right for this particular moral schema, okay? And so in the normative or normal state, the average values of appraisals would be equal to feelings. That's the definition. Now, if we go to more formal description, we can say that the moral schema includes certain parts like interface, fabula, agency, and so on. I'm not going to describe in detail now what does it mean, but here are some examples of moral schemas, maybe simple examples, like a human line where there is a certain order in which people stand in front of a counter, and they, in a sense, have a hierarchy, who dominates whom, and they maintain this hierarchy. Or there is a mutually, there is an exclusive partnership of two people, or there is a violation of this partnership which results in betrayal, or there is a subordination of one person and another. And these kinds of relations are described by the formalisms that I just mentioned, moral schemas, which means assigning certain values of feelings to each actor participating in this relationship and computing their appraisals based on their behavior, comparing the two. And if there is a discrepancy, then we need to do something about to restore the normal state. Okay, this is the life cycle of a moral schema in which it is first extracted from semantic memory and gets bound to the current situation. Then it activates and operates under normal conditions. When it comes to a discordant, dissonance condition, then we need to resolve this dissonance by either modifying the values of feelings, which changes the configuration of the schema, or actually moving it out of the current perspective to another perspective, and eventually we can deactivate it. But it can be also deactivated because the conditions of its applicability will terminate for some reason. Okay, this is just in brief. As I said, the principles of operation is minimizing the difference between appraisals and feelings, which is achieved by all possible means and can be very complicated. So the principle is very simple. The implementation can be very complex. That's the idea of a moral schema. And now if we, let's say, have an agent controlled behavior of which is controlled by moral schemas, it can proceed as follows. Like we have one normal schema that achieves its normal condition, then it activates another, which achieves next normal condition and activates the third moral schema, and therefore we have executing a certain scenario which in itself can be called a complex moral schema. So this is how it operates. You see that for the transition to happen, the values of appraisals must take certain values in this semantic space, and these values are actually determined by intentions of the actions, plus certain hard conditions that also need to be satisfied. So this is the general idea, and I'm not sure how much you got from my words, but given the time, this is probably as much as I can tell. The principle of operation of such agent is shown here. Now, if we build agents of this sort to interact with human users and to do some practical tasks, then here's how we need to proceed. First, we need to do some semantic analysis of the speech act of the user, extracting intentions and intentions, feed them to moral schemas, use knowledge and rules to compute the optimal behavior, and based on that result, we again need to define intentions and intentions to be expressed in the response of the agent. Now we need to convert that into a prompt for generative AI, and generative AI can perfectly do this task and generate an answer to the user which would tell what we need to tell, and with the tonality that we specified, determined by those intentions. So this is in general how it works, and an example of such system is actually our virtual tutor system that we built recently, and hopefully you will see this system in action on Saturday in our demo, in which case it will not be doing tutoring, but will do a discussion panel on the future of AGI. Well, I hope people will enjoy it. Okay, so the conclusion is that we constructed a mathematical model of the semantic space of intentions, including 92 dimensions. We connected those intentions to moral schemas, and we, in general, come to conclusion that BICA, when integrated with large language models in the described way, can allow us to overcome the limitations of large language models. Thank you, and I guess I still have time for some questions.
Thank you for your presentation. Any question? Okay.
Hello. Thank you. I really enjoyed your talk. So I have a question that may be a little controversial, but do you think that by having this kind of model that you would be able to optimize to create quote unquote personality of agents? So this is within the context of some folks want to create agents that can kind of interact in a more social way with humans. Do you think that this could be the start of that kind of way to optimize for certain personality traits, whether they're negative or positive? Thank you.
Yes, this is exactly the goal of this research, to create something human-like, having a soul in the human sense. And by the way, it's not so difficult to create an agent with a certain personality type. There were numerous attempts of this sort, but here we need to go beyond that. We need to what can be called human mentality, like what's on the mind of of the person with whom you communicate, and how you can represent your own mind so that the person would perceive you naturally and believe that you understand the relationship and the situation. And yes, there are many aspects, many questions here, but I am convinced that only BICA can give those features to AI, because generative AI, in a sense, hit the ceiling where it does what it can and cannot do more. It cannot have a soul on its own. It cannot have like free will or goal generation. Well, you can try and get some possible outcomes of that sort, but I guess that would not be what people would want to see. They need something human-like, something that humans can understand, can trust, and can accept as their own kind. And that can be done, I believe, only with BICA.
Thank you. We have another question.
Thank you for your talk. It was really interesting, and I think gives an overall perspective of what to look into and things to work on. Very, very interesting. So my question is, thinking about the semantic space model, where you have the space 1, space 2, space 3, and then you have x1 up to xn. So the question is, should we look also into, how many, let's say, I don't know, semantic spaces to consider for an artificial agent to be, human, or as close as we humans are, and also in terms of the variables, the number of variables. I mean, seems that if we develop a model, I mean, we can never end, in terms of the
Yeah.
of the number of
Yeah, I
variables.
got-
And computationally speaking, again, when it comes to scalability, and when we develop this artificial world with the agents, I mean, is it really something to look into in terms of doing the analysis of how much to put into the model and how much we can get out of the model?
Yeah, thank you. Thank you very much for your question. Unfortunately, I cannot tell you too many details because of the limited time. The idea is that we build a general model of semantic space that includes all dimensions that we may need in all reasonable circumstances. And that model may have possibly thousands of dimensions. I do not know. Actually, this is an interesting question, how many of those dimensions are. But for each particular situation, and therefore for each given moral schema, we need only few dimensions. So we have a space, a subspace of this huge space. And this is what I call by space 1, space 2, space 3. Those are subspaces in this huge hyperspace. And we make transitions from one subspace to another. The general model already gives us the tools for defining those subspaces and computing transitions between them. in this sense, it solves the mathematical problem. And yes, I agree, it deserves more research and needs more ideas to develop in this direction. Yes, thank you.
Thank you, Professor.
So I would sorry, I wanted to make also one analogy between this huge semantic space and the soap. You know, there is a quantum soap of Stephen Hawking, and this is a semantic soap where you have these patches of subspaces related to individual moral schemas and types of situations that are connected to each other and form a global mesh or network or soap, if you will, with bubbles, and each bubble would be a moral schema, and they are connected to each other with such transitions. And this is how our general semantic space may look like. But this of course needs to be validated, this idea.
Hi, Alexei. This is Ricardo Goodwin here.
Hi, Ricardo.
I was wondering, when you use this notion of soul, if it's not going to be a self in the term of consciousness, and in some sense you're touching at least some issues of consciousness when you think about this soul or self. Because when you talk about moral schemas, in some sense you are making the relation between different selves. So one self do something and the other receive something, and all the examples that you showed here, in some sense, at least to me, appears to be touching this issue of consciousness, at least indirectly, if not directly doing that. But I don't know. I'm just wondering here if you're not touching this issue of consciousness with this idea of a soul or a self.
Absolutely, I agree. I am touching this idea of consciousness, and this is one of the objectives which I did not elaborate on because of the limited time, and I didn't want to dive into philosophical speculations, but actually I'm very, very much interested in this problem of creating artificial consciousness. And of course, I consider this approach as a way toward the artificial consciousness. What is a self? Actually, there are several notions of a self. One is the core self, which is immediate, this moment self, and it is nothing but a perspective from which the person perceives the world. It's the identity of the person, the location and space, time and context, the status of the person, relations to everything else, and how is it looking from inside everything for this particular person. That's what I call perspective in this model. And each moral schema comprises a number of such perspectives that interact with each other. In a sense, it describes interactions of the selves. But the large notion of self in psychology and sociology, of course, relates to development of self over time, the personality, personal memories, interactions with others, relationships. And that is also a big issue, like how do you develop personal relationships in an artificial agent? How do you represent them? I do not see any alternative to moral schemas or something equivalent to them to implement personal relationships. What I actually did not say and would like to say now is that these things that I described are symbolic in the sense that they are proposed to be implemented by hands, engineered based on psychology, neurophysiology, whatever. But eventually you can transfer them to a neural network. How? You create a BICA engineered by hands, generate a huge amount of data with this BICA in some virtual world, and train your transformer on that data, and then this transformer will implement your cognitive architecture. You may not know how, but it will do just that. And then it will be able to grow beyond that point at which you trained it. So that's the actual interesting idea, I think.
Okay, thank you, Alexei.
You're welcome.
Well, thank you so much, Professor Alexei, for your speech. Okay.
Am I done? Thank you.
Yes.
Thank you for
Thank you,
inviting
Alexei.
me. It's a pleasure to speak at such great meeting.
We're glad
Thank
to
you
having
all.
you today. Thank you.
Bye-bye.
So let's continue with the next presentation performed by Oscar Guadalupe.
Okay, good afternoon. My name is Oscar. I'm going to present you a computational model representation of TATSET based on cognitive science evidence. In first place, this is the content of the presentation. First, like an introduction, show you some concept or keywords for this work. Planning, say the plan is a process of defining a course of actions and procedures required to achieve goals and objectives. One concept important is also a decision making. That is a useful process for selecting an action from a set of able alternatives based on a given criteria or alternatives. To handle these situations, people use a cognitive process named TATSET. TATSET is an important concept for this work. Charlie, can you please take the... Thank you. TATSET is a configuration of processes that are initiated when an task is started and continues until it is finished or abandoned. The definitional problem, a computational planning and decision-making system face difficulties in dynamic reconfiguring the process of plan preparation, retrieval, and selection. And this is an open problem. Like objective, this paper proposed a computational model of TATSET using evidence from cognitive science. Like motivation, these are possible implementation in problems in real life, like simulation, video games, and natural disasters. Like biology evidence, we have some systems, 4 systems. In first place, we have the percept systems. And second is attentional system, motivational system, and emotional system. These systems are black boxes. That means that we simulate the output, the process, and take the outputs. Also, we identify some related areas, brain areas, like ventral-prefrontal cortex, anteroprefrontal cortex, ventrolateral prefrontal cortex, dorsolateral prefrontal cortex, prefrontal cortex, posterior parietal cortex, anterior cingulate cortex, and so on. These areas is configured that all the process of TATSET that in the next in the next slides we are show you. Okay, this is a conclusion. This evidence that the cognitive function of brain areas previously described provide an initial understanding of the process and stage of the TATSET process. Based on biological evidence, it is confirmed that the connection proposed in the TATSET model correspond to those in human brain. We investigate some cognitive architectures related with this concept of task set. We look for this and see that our architects like Lira, Sword, Cube were analyzed to identify how to implement the concept of task set. However, none of them explicitly use the approach of task set. Although the state of the art of the task set process is reached, there is currently no consensus on this process in a computational model. Tasks allow to achieve better scalability, adaptability, and the reuse of knowledge to apply to solve other tasks. This article contributes with a cognitive science inspiring the computational model of task set. Like proposal, we propose a model based on all the evidence on, recollected. Propose this model of task set that is a conceptual model and show a general overview of how to work this model. In first place, we have the systems, the 4 systems that are black boxes. These systems propose a layer. That layer is a representation of the task and show you what task to perform or what task to be performed. This task is composed by another possible subtasks and depend based on the type of task that we are resolved. And this information is passed to the core of the task set process, and that is divided in 3 stages. Stage 1, preparation, retrieval, and selection. This is a little based on the common reinforcement learning, and is the core of propose. In first place, the preparation of the object of the preparation stage is to identify what plans or what decision can be proposed to resolve the task that present us. For this is the common familiarity criterion to select the better planning sets. This planning set is passed to the next stage, and this stage is in charge to select only one plan. This only one plan is the better plan based on some criteria like utility values and motivation, representation of the motivation, etc. In the last one, the selection, here is in charge to execute the plan selected based on some criteria and use some rules. These rules propose the way that take based on the stimulus of the task or the state of the task to select different types of rules. When you execute this plan, obtain a reward after of one evaluation or reward evaluation. And based on this reward evaluation, depend if I select other decision, I select another plan, or I select completely another planning set. Like case study, we propose this structure to planning set. In the first place, planning sets, we use for this occasion or for this case study, a task called match no match. It's like even or odd game. This planning set have a value utility and also have different plans. These different plans compete between them to be selected. Each plan have different rules. That rules is association between stimulus response or stimulus and both response or different response. Depend the level of complexity of the task. First place, we have a stimulus, the analysis, and the action. and have a utility value that is evaluated based on the utility of the response or of the action. For the utility calculation, we use this formula. It's a easy or simple equation that is a weighted sum that it uses to select the best utility. This is the game used for this case of study. This is a match no match. The objective of this case of study is to validate some aspect of that model. And three fundamental aspects are or can be evaluated: the correct population of plants, the retrieval of plants, and the self-shifting of the plants and rules. This task consists if the two figures in this frame are similar, select left, and if they're different, select right. In the match rule, the responses are inverted. And the model should be capable to change of rules or use another plan. For the value the model, the instruction can be presented in two ways, inductively and deductively. When the task is instructed to be performed, and deductively when the task is not instructed to be performed. And for the case 1, 6 trials was proved. The plan is changed each 10 trials, and based on the familiar criterion, select the correct response. In this case, the model don't have problems to select the correct answers, and continue 6 trials in this proof. For the second case, is deductive. Also have 60 trials. The plan is changes 10 trials, and the familiar criterion was not used because the model don't know what task to perform. The model deduce what or propose some plan, and based on the regular value, change or not or give the same plan. In conclusion, in current work, a computational model capable of reducing knowledge is in similar tasks, adapting to dynamic environments, and identify the different types of tasks is a significant achievement. It's important to evaluate a model across a more expensive range of tasks, guided by a comprehensive taxonomy of the task types. This will facilitate an assessment of its generalization, capacity, and adaptability to a range of dynamic environments. And also have another current word that is multiple planning set. We use multiple planning sets for that model. And that is all. Thank you.
Thank you so much, Oscar. Does anyone have some questions? Okay.
Hi. I was wondering, in this model that you created, if there is some change in the world that requires some kind of replanning, because, for example, the old plans are not feasible anymore. In your model, it is possible to have this possibility of replanning, or after you plan and you put it to execute, it needs to end the full plan?
The principal idea is that the model have the capacity of flexibility. Don't stop the execution, and always propose a new plan. Propose a new plan. Don't incur the plan is incorrect or are optimal.
So you cannot abort a plan in the middle of it, in the middle of its execution.
No, the importance in this model is that always that the model don't stop to know what plan to propose. Always have some for familiarity. Don't be exactly the plan, but for familiarity, probably have the a plan can resolve the similarity task. And is the principal idea of this model.
Okay, thank you.
Someone else?
So with the task sets, if you're given an individual task, are you breaking that task down into task sets, or are you assuming as an input off the bat you have a task set to plan around? So are you decomposing a task into a task set, or are you given an input of a task set?
We have a task set for one task. And the task set is composed by different planning sets. That planning set can resolve some aspect of that task.
Okay. So so you have a task set for each task, and for the individual tasks in the task set, those could be shared across multiple tasks, right? Meaning that you have some kind of sharing going on between the objectives that you'd be doing.
Yeah, one of the proposed is to differentiate by a taxonomy the different types of tasks for not generate that confusion of the level of different tasks. Is a task of or a big task, or is a little task that require not require effort or is easy task. But it's one of the proposed or the future work to make that taxonomy for the different type of task.
Okay. Let me see if I can. So I have actually a specific question I was kind of trying to get into. So you assign a reward for each of the individual elements in the task set, right? If you're reusing those different elements across different overall objectives, would the reward be a fixed amount since it's really in service of something else? The contribution of that particular subtask seems like it would be variable across different task sets, if that makes sense. So for example, opening the door over there may have some small value of reward when it comes to going to the hotel or something like that, right? It may be more important, a higher reward in a situation where there's like gold outside of that door. So the contribution of the only way to get there to the gold is to go through the door, and it's right there, and that's the only way to do it. It might have a higher value than if I had multiple options to get to some other location with lower ultimate reward value. So I'm not sure if that makes sense, but from what you were saying earlier, it almost sounded like there was a fixed R in your equation for each task in the task set.
Mhm.
Okay. And do you think maybe if you were to enhance it, there'd be some variable amount of reward given the overall objective of the task set?
Okay, one of the things that difficulties that's models of planning and decision making is the reusing of the information or the knowledge for resolve one similar task to another task probably or for another task set. And one of the proposed for future work is to propose a generalization of the information of the decisions. Open the door or only open, and that definition of open also or reuse another task. For open a glass, open a can, etc.
Okay. Yeah, I think I recall something from hierarchical reinforcement learning of pseudo rewards for these different components that don't themselves have value, but they contribute to a larger thing that does have value. It sounded like you were kind of getting into something similar to that, but I may not fully, I haven't maybe fully digested everything, but it seems like there's a problem of, kind of so these things themselves don't have value, but they contribute and they have instrumental value towards something. And it seems like there might be some variability in the reward you'd want to assign to those things, particularly if you allowed interruptions in your task set to pursue some other task set. Thank you.
Thank you. Thank you.
Okay, dear attendees, we're about to finish the session for today. So let's begin with the last talk performed by Amit Madani. So Amit, go ahead.
Yes, thank you all. Lovely talks and topics. Yeah, so this is about my work of the last 2+ decades and what I call prediction games. And it's a status report. It's a very quick summary of the newest ideas. So I'm going to start with motivation and then the different parts of the techniques and the whole context, and also compare it very briefly what you can do with these and compare it to large language models and neural nets. Okay, so what do you see in this picture if you haven't seen it before? So I got this from Eric Kandel's book. He got it from somewhere else, Reductions in Art and Brain Science. When I ask my colleagues, usually they don't have a clue. It looks like a map or something. How about here? I had a conjecture that if you make it smaller, it gets better, you can reckon it, but I haven't found any evidence of that. So if you can make sense of this, interpret this. How about this? This should help now. This is the same thing as before, so you can see the eyes, the nose, the beard, right? I think now you can see the correspondence. So yeah, the basic question is how does our minds put pixels together, shapes together, make bigger shapes, and until things make sense to us? How does our mind do this so rapidly? How does it map it into internal concepts? This is kind of like a loaded question, right? What are concepts or internal concepts and so on? So, but that's the motivation for my work. Yes, and you can see another fun picture of this is, I guess, a vent worm, Nereus thunderisi, 2 mm deep sea worm. But you can't help but see the eyes or interpret it as eyes and the mouth and fun. Okay, let's start with the code that I really excerpt that I really narrowed to the most important parts for I think from Medine, Ross, and Markman, cognitive psychologists from their preface that any visual input is consistent with an unlimited number of interpretations, and it's a miracle that we come up so quickly with some small number, usually one. And these sorts of expectations or constraints occurring in all facets of cognition. And also that from Gregory Murphy, that concepts are the glue that hold our mental world together. But indeed, they are maddeningly complex. So for me, intelligence is a finite mind repeatedly interfacing with infinite world, a changing world. And infinite is because of all the possible interpretations that one can have. But the mind is finite, it has finite computational resources, finite memory, limited time to decide and act and so on, and sense and so on. And cognitive psychology tells us that human intelligence rests on concepts, such as table, water, mother, life, mind, mad, and so on, and many such, and they are operational. In machine learning, we usually do classification or clustering, but then it's the end of the day, we just classify. But no, these things influence one another and develop together, and they are used together in making sense of the world. So, and looks like we get them in a basically unsupervised. It's not like teaching or language, or again, not like supervised learning. So how do we get that? Do you agree even that we have concepts? And if you do, there might be disagreement about what the details are, what the representation of what a so-called concept is. But for me, the question has been two. One is snapshot in time question that was early in the morning was mentioned. Given a scene and a situation at time t, how does our mind quickly narrow down the set of important variables, interesting variables? Call it down to the agent's few concepts from many thousands or millions available in the head, right? How is that achieved? And then historical or longitudinal or developmental question, where do these many concepts come from in the first place? Richly interdependent. What processes can support this? And so prediction games is a way to address aspects of these two questions, and it does it we do it in this approach simultaneously. These two questions are, in a way, out of some maintenance. So PG's, the lesson is that the message to take from this talk is systems that build their own patterns, concepts, representations to be predicted and to help predict. So we call them concepts, and these concepts are both predictors and predictants, targets of prediction. And they serve as Legos too, as building blocks. So the other names could have been proto-concepts, percepts, or construct patterns. So DOG has the concept DOG, D-O-G, the letters D-O-G, I'll be talking about letters and text mostly, or it has out edges. These are the prediction edges. What other concepts is predicts, but it has also in edges, similar for the cat. And the relationships could be reciprocal. There could be cycles. A dog could predict itself to come next. Also, they have incoming edges and outgoing edges and different types of edges. There will be some edges that are about the parts that activate the concept DOG, dog. So the prediction game systems builds these hierarchy. And so it relates to constructivism of Piaget and others. At the perceptual level, at the time where you interface, the agent interfaces the infinite world, which you should not take lightly, I don't think. That perception is very deep. So different edge types, network ends. So overview of the prediction games approach. You have to start somewhere. So you start with a set of primitives. These are the hardwired, the givens, an alphabet, a finite discrete set. That's V at times 0, V0A. And then you repeat indefinitely. You input a line of text, one-dimensional for now, and interpret. The system interprets it. Which of my concepts are useful here, where, how, what relations, what configuration, and then learns from that. Learns from interpreting, expanding and enriching its network vocabulary, edge and network N. So this cycle of interpret, learn continues indefinitely. Network N is rapidly updated, edge is added, deleted, and the V grows from time to time. The set of concepts, the nodes in the network grows. So as if it's nature or evolution or engineer designer says that, okay, I don't know what the world what world you will face in your lifetime, but here's a V0. Some experience, maybe past life, shows that V0 is a good starter kit. Plus a few algorithms and learning algorithms, inference to go with it, some appropriate hardware. Now you're on your own, learn, adapt, expand this V, and make it work. Good luck. So again, for the repetition is, I love visiting Mexico, for example. You sample a line from corpus of text. That's the current expedition system, and one instantiation of prediction games. That, you sample a line of text from your big corpus, you interpret it, you learn from it, and you go on from there to the next thing. So, or another way to view it, again, there's a stimuli, the eye, and sensory processing, complicated. You map it to a sequence of primitives, that impressions, you map it to a sequence of primitives from the alphabet, the initial, the primitive alphabet, the givens. Then the game starts in that episode. This is a single episode. Invoke higher level concepts and match, predict. Invoke lateral concepts, higher level. You start from one position and randomly say, you do this interpretation back and forth. And invoking and matching are both prediction, or at least I'm working on unifying them to basically be prediction. Match is definitely prediction. Invoking is the kind of prediction. And that's the single episode, and then repeat this. So interpreting is fundamental to so-called semiotics research and activity, and we can the study of science systems or meaning making. And maybe this work can be looked at as a computational story for that. Okay, so you interpret better. What is that? What does that buy you? It gives you more better prediction because you're going with your high-level concepts that predict better, and so that will let you live longer. And if you're going to structure the world, your input stream meaning at some point in your lifetime, why not practice doing it all your life? Because you're going to do it. You want these structures to help you, right? So why not practice doing interpretation? So development is achieved through systems learning. Again, from beginning of the paper I published in BICA more than a decade ago, it talked about systems learning, multiple algorithms. I don't think there's one single algorithm that does all this, but the question is what algorithms, how tightly integrated they should be, what What is the objective or the objectives? Would it not face, combinatorial explosion, or would it not get stuck in local minimum? Yeah, these are the challenging questions, research questions. But again, the picture is development of PGs. You start with a basic that only has concepts at the primitive level. After many episodes, it can make better sense of its world by breaking that same episode even to different higher level concepts, because its concept vocabulary has grown. So the same episode, if it looks at it years later, it sees it differently. It will still see the pixels or the low primitives, but it has higher level concepts too. And right now, we are limited to n-grams, sequence of consecutive characters for concepts, for the representation power of the system. And so a concept is a controller structure. Once it's activated, it says, hey, I'm going to predict the beginning and whatever is not covered. You predicted me, let me now take over. But it's a network, it's a node in a network too, so it has edges to other concepts, predictor and predicand. And core allows us to do good, approximate matching and so on. So it's not exactly n-gram, it's a little beyond, but it's not much beyond conjunction at this point. But core handles approximate matching. So now the canonical NOW doesn't have to appear for the concept to get activated. And sometimes NOW does appear in the system in an input, but does not get activated, does not lead to activation. These edges are probabilities, as you gathered, and actually semi-distributions. And we have code, and now it's publicly available for sparse moving averages that handles learning these probabilities in a non-stationary world. The concepts create non-stationary. The outside world could be non-stationary, and so on. And that actually ties to my earlier talk that talked about agent. We use similar algorithms for that agent. So we are working on unifying the vertical and horizontal. This is another example of a concept, THER. Before it can O, like other, after it, like E can happen with some for there, and it's holonym, and so on. So how about concepts and interpretations? In an episode, you can have primitives that activate concepts. Concepts are sequence of primitives. And then you can have sequence of concepts that make an interpretation, and then the input buffer, all of it or some of might be multiple interpretations. So the givens are these, and the constructions are the ones that the higher level concepts and interpretation are constructed. Some of them on the fly interpretation can be thought about as thoughts, as fleeting thoughts, macro thoughts, perceptual thoughts, stories. Concepts are, persistent for some time or for the rest of the life of the agent. And so core is originally developed to motivate why should a system build larger concepts, but now it's also useful, can have different interpretation. It's a good summary of a combiner of context and matching to the lowest level, primitives level reality. How much
Omid, can you hear me? Okay. Okay, we have lost connection with Omid. So, hold on, please.
Am I back now? Am I back now?
Okay. Is everything okay?
Back now? Yes. Am I back?
Okay, continue, please.
Sorry about that. And I hope I was in this slide when you lost me. This is an example of interpretation. Basically, you start at the primitive level, no edges, isolated interpretations. Then after some time, n at 100, you see the edge probabilities. These are horizontal edges, and an interpretation could be one interpretation, but singular elements. Then at some point, n 200, you're going to see vertical edges, and so on and so forth. And eventually, you're going to learn the ABC as one concept, and ABD. and you have more vertical edges and so on. But here's an interpretation. A gets activated, then AB, then ABC. We continue to work on new concept incorporation and interpretation search techniques. Findings. So we have, through the years, I've gone from words as your vocabulary, like 10,000 words, to characters. Now I'm testing with even lower level, like 10 characters. 10, each character is encoded into 10 possibilities and so on. And even binary, only 2 primitives. To test, the algorithms, to stress test them. When do they fail? Can I improve them, and so on. So here's an example, encoding in 2. So each character is encoded into 2 lower level alphabets. So initially the alphabet has 10 symbols in it, 0 through 9, say. And so every odd split is bad, every even split is good. Does the system recover, interpret, when faced with this encoding, not knowing what the original characters are, does it recover the original boundaries, good boundaries at characters, right? Every odd, so 50% is the random. At the beginning, it has 50%, and it lowers it to near 0, to below 0.05 with current algorithms. We were working on improving the algorithms. And let's compare it to language models. This is unsupervised, so it doesn't need Y. It doesn't need pair X and Y like a neural network, right? With backprop. Just give it the stream. It says, I'm going to make my own concepts. It structures its input through interpretation to do so, and outputs a structured concepts. For analyzing unknown words, let's say you're some language or some animal behavior you want to know. Yeah, you need to decide on the primitives, but the primitives doesn't have to be that informative. And it's very interpretable, right? The concepts are the canonical form, what neighborhoods they are, at least now, currently, so far. And then you can look at the interpretation and give an episode, what concepts get activated, and so on and so forth, what concepts have been selected. So it's interprets and it's interprets. And
I can hear you, Doctor.
Up again.
Omid, is everything okay? Well, we have just lost the connection with Omid, so maybe we can conclude, or you want to wait for him? Okay. Let's wait for Omid 1 or 2 minutes.
Hello?
Yeah, I hear you, Dr.
Yes.
Omid.
So
Yes.
that's basically, that was it. Basically summarizing the comparisons and how we can use prediction games. They are interpretable neural networks or not. At this point, you can say when in an episode, what the system sees. Yeah, so I call it agent friendly. These systems can learn online. The structures that they learn are shallower. They can be updated, so non-stationary and so on. But we need to explore these things in robotics, in agents, and so on. But I'm also thinking that, yeah, the learning, the sample complexity will be much more efficient. It wouldn't have as much catastrophic focus because things are modular. Thank you for your time. Again, intelligence is about finite minds touching infinite worlds, so proceed with caution. And prediction games is a way of doing online cumulative learning. And so far, we have gotten some ingredients promising, like a core for guiding the search and a sparse moving average for prediction edges, working on details of what's a good interpretation search and so on. But the major open question, I think, is the learning disjunctions, not just conjunctions, not just engrams, but having more abstraction inside concept and structure. And I also believe that this approach is more agent-friendly, learning on the fly, online learning, continual learning. And also for symbolic tasks down the stream, like planning, reading episodic memory, and so on. Hopefully within a year, I'll have an update to the paper for interpretation. Thank you so much for your time. Apologies for breaking up.
Don't worry. Thank you so much, Dr. Omid. Does anyone have any questions? Okay. We have a question.
Hello, Omid. I was a little bit, let's say, I'm a little bit confused because in some of your examples, it seems that you are trying to address the problem of meaning of some words. Another example, it seems that you're just making the sequencing of letters into words. And
yes. It's not natural language. It's after some time, in first few years, I decided this is more for perception. So it could, I would love to go into 2 dimensions and make it more perception. So basic structures. Then we need more processes for, higher level meanings, such as abstract words like, mind and life and so on. But this is for, at least at the perception level, some system that gives you the basics that you can name afterwards, some of the concepts, not all the concepts. Yeah.
Yeah, but some of these letters, they don't have an intrinsic meaning, and other ones they have. For example, ing, it means the infinitive of the verb. Some others, they do not carry this meaning. So it seems to me that at some points you are trying to address this problem of meaning, and in other points you are just being very nominalistic and trying to just make a distinction to different kinds of words. So this is something that made me confused.
So here's what the nature of the designer gave the agent the primitives and said, I think these going to have some meaning once you combine them, especially. Now, some of them may never get any meaningful interaction. Some might, they might combine well to get much more predictive. So like ing getting together or a and d and so on. So you build this hierarchy and the meanings are inside this system. But then there could be other meaning for meaning, right? What is the consequence of all these structures that I'm learning and all the edges between them? Let's assume you have another channel that's like, let's say it's your reward channel. Whenever one of these words appear in what you see, you get a reward. Like if you do eating, this is going to do what we're going to do, is you associate, you say, oh, when I see F-O-O-D, food, not when I say F is too generic, but when I see food, I get food, for example. So there's another meaning, the meaning that this thing not only has predictions around it, it constrains what comes next and before, but also it's associated with some life-saving things. So some things could be dangerous, some things could be costly, some things could be rewarding. You across channels, right? Across sensory channels.
Yes, but how?
But you started with very low-level characters or primitives like pixels, 0 and 1. Yeah, go ahead.
But how do you ground this in characteristics of the world, for example? But you're not talking about that in your model.
Yes. So yeah, this is like a closed, if in that sense, if you want to say closed world, in that sense that the characters and the words get their meaning from each other. But grounding might mean that hey, what is this useful for? What are all these things that you build? Like you went to university or something, you learned all these abstractions. What are they useful for? Then you need to also associate them with food or with, and I'm assuming that these things can be done, from one channel to another very quickly. By a few exposures, you'll figure out which of these things carry the most significance. But the other meaning is the distributional meaning. Within text, the words have meaning by the fellows that they keep. That's what is captured here, I think.
Yeah, when I'm talking about meaning, I'm addressing the problem, for example, that you're using words from different languages. So you can talk about food, but you can also talk about comida in Spanish. And the meaning of them is going to be the same, but the words are completely different. And at some point, you need to ground the words in these meanings that will be transparent to the different words in different
yes.
languages.
I see. Yes. It's going higher and higher level. At some point, yes, food will come in the English channel. Let's say you have a different corpora, and let's say the system is smart enough to figure out, hey, I'm dealing with different languages. Let me not mix up the edges. But at some point, it must say, hey, food and comida is synonymous. They mean the same thing in two different languages. Yes, that's very high level, but again, I think this approach has the potential to get there. Yes.
Okay, thank you.
Yes. Thank you.
Amit, this is Luis Leiva. I have a simple question. When I look at your presentation, it seems to me like information theory.
Yes,
exactly. Is that correct?
Yes, it's very probabilistic. And right now, the major way that I connect different characters and bigrams and trigrams is based on core, which is very information theoretic.
Okay, thank you so
Exactly,
much, Dr. Omid. That's all for today. And we kindly
Thank
invite you to stay in the common area for a toast. And thank you so much.
Thank you.
For the virtual attendees, we look forward to seeing you in the virtual room tomorrow at 9 a.m. Thank you so much and have a nice day.